Tes. 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 Ladies and gentlemen, in 5 minutes, we will begin the opening ceremony. You may now take a seat. Please, participants, rename the name according to the rules. Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. All praise and thanks to God, the Lord of the universe, the Master and Creator of everything in this universe, for His mercy and blessings in allowing us to meet and assemble this morning without any difficulties or barriers. Ladies and gentlemen, I would like to send a warm greeting to all of you who are attending our major event, the second International Conference on Chemical Engineering and Applied Science on November 3rd, 2021. I am Zahra Nurjanati Korina here. Being a master ceremony in this group program is a lovely and precious opportunity for me. Let us pray together before we begin this event. May God will make this event beneficial to all of us and that it will run smoothly and efficiently. Start praying. Finish. Now let us hear National Anthem of Indonesia, Indonesia Raya. Please participants stand up and also we will hear Diponegoro University song. We have several agendas on this special morning, so please allow me to read several sequences of our agendas. First, registration. Second, opening. Third, welcoming speech from speakers Diponegoro University. Fourth, speakers from first and second keynote. Fifth, sharing session. Sixth, lunch break. Seven, parallel session 1, and the last is closing. Now we will move on to the speaking part, which will begin with a welcome address. Speakers from Diponegoro University are cordially invited. The Excellency of Chairman ICS 2021, Mr. Hermawan Dwi Arianto.
Your Excellency, Rector Diponegoro University, that represented by Vice Rector of Research and Innovation Diponegoro University, Professor Ambarianto, all of the deans from Diponegoro University, Dean of Vocational School, Diponegoro University, Professor Budiono, keynote speaker, guest speaker, moderators, and all participants, ladies and gentlemen. Very good morning from us from Indonesia. On behalf of the organizing committee, I would like to extend our warm regret to all the participants at the second International Conference on Chemical Engineering and Applied Science, ICCS 2021. Due to the safety concerns, ICCS 2021 is taking place in a virtual meeting. The ICCS conference is expected to design an interactive international forum to provide the platform and the sharing information in the latest research on the chemical engineering and applied science. With the successful history of ICCS conference in the previous years, we are committed to provide the high quality international conference with the collaboration with industry and the community research around the world. We are also proud to thank the presence of the keynote speaker, invited speaker, and all participants who are joining the International Conference ICCS 2021. As a chairman, I would like to take this opportunity to thank the organizing committee, the Dean of Vocational School, and also my students who also help us to preparing the international conference. For last but not least, I would like to thank the co-university, especially Shah Kuala University, Rio University, and University Technology of Mara, Malaysia, for guiding us during the preparation of this conference. I sincerely hope you will enjoy today and the next day conference, so you can gathering with other participants and get the positive value. Thank you very much.
Thank you for your welcome remarks, Mr. Hermawan Dwi Arianto. Now I'd like to extend a warm greeting to the Honorable Dean of Diponegoro University Vocational School, Professor Budiono.
Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Alhamdulillah wassalatu wassalamu ala rasulillah la hawla wa la quwata illa billah. The Honorable Rector of Diponegoro University, Vice Rectors, all deans, Head of Department, Head of Study Program, the Honorable keynote speakers, invited speakers, and the Honorable Organizing Committee of ICCS 2021 and distinguished guests all participants, ladies and gentlemen. First of all, Alhamdulillah, let us thank Allah, the Almighty, who has given His grace and guidance so that the second International Conference on Chemical Engineering and Applied Sciences with the theme of Designing Tomorrow towards Sustainable Engineering and Technology can be held successfully. I welcome all of you to this conference, which has received great attention not only from university, but also from scientific community to submit papers to be presented in this conference. I express my highest gratitude and appreciation to the presenters. I believe that this conference will be the source of innovative ideas, concepts, and breakthroughs in the development of chemical engineering and applied science area in the future. This year, the second International Conference on Chemical Engineering is organized collaboratively by Vocational School Diponegoro University together with Chemical Engineering Department, Syah Kuala University, Indonesia, Department of Chemical Engineering, Rio University, Indonesia, and University of Technology, Mara, UITM, especially Faculty of Chemical Engineering. As we know, the format of ICAS 2021 conference is different from the previous years through full online meeting, as we embrace a new normal, practicing safe social distance due to the COVID-19 pandemic. Please accept my sincere thanks to the excellent contribution provided by co-host universities, Syah Kuala Universities, Rio University, and UITM in supporting ICAS Conference 2021. I believe this university partnership in holding an international conference will have positive impact for its institution. I hope this excellent collaboration between four universities in ICAS consortium can create better mutual collaboration, such as research collaboration to create high impact research and publication for our researchers and students. We may expand this partnership to other institutions who have same vision to make our community better in the future. I believe that this ICAS 2021 will bring the best in terms of researchers, technology, and science on international scale to increase partnership and cooperation, and to share research progress between universities, institutions, government, and small to large scale industries in order to advance the science and technology. Congratulations and sincere thanks to the organizing committee for the tireless effort and hard work in ensuring that this ICAS virtual conference is conducted smoothly and successfully. To the presenters, I wish you all the best and have a great scientific forum. Lastly, I hope all participants will find this virtual event to be fruitful with wonderful moments of knowledge and experience sharing. During the conference, bila taufiq wal hidayah. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh.
Thank you for your welcome remarks, Professor Budiono. Now I'd like to extend a warm greeting to the honorable representatives of Diponegoro University Rectors, Professor Ambar Riganto.
Thank you. Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Very good morning, everyone. Honorable keynote speakers, honorable invited speakers, Dean and Vice Dean of Vocational Schools, dear friends from Syah Kuala University, from Rio University and University Teknologi Mara, Malaysia, Chairman of the second EGCS 2021, distinguished delegates, colleagues, researchers, scientists, industry representatives, and all participants. First of all, let's us pray to the Almighty God for all His blessing, grace, and mercies that have made us possible to gather here in the excellent condition and health. Secondly, on behalf of Diponegoro University, it is my great pleasure to welcome you all to the second International Conference on Chemical Engineering and Applied Science with the topic on designing tomorrow towards sustainable engineering and technology. This international conference is held every 2 years to accommodate academic and professional communities to discuss and exchange ideas. Previously, it was known as International Conference on Chemical Engineering and Sciences and Applications, which was held by Chemical Engineering Department, Syah Kuala University, Indonesia, together with the Faculty of Chemical Engineering, University Teknologi Mara, Shah Alam, Malaysia in 2017, a couple of years ago. As mentioned by the Dean of Vocational School this year, the second of EGCS is organized by collaboratively by Vocational School Diponegoro University, together with Chemical Engineering Department, Syah Kuala University, and Chemical Engineering Department, Rio University, and also the Faculty of Chemical Engineering, University Teknologi Mara, Malaysia. Ladies and gentlemen, the aim of the second EGCS is to provide the most advanced and comprehensive global forum for disseminating results and data in research, development, and application in chemical engineering and applied science area. I believe that this event will be a good place to share your recent discoveries, as well as to build partnership among us so that we can move closer to answer the challenge related to chemical engineering and applied science issues. In this opportunity, I would like to congratulate the committee for successfully preparing and conducting this international seminar. And again, my special gratitude goes to keynote speakers, all participants, and all other parties who supported this event. Finally, ladies and gentlemen, with the permission of Allah Subhanahu wa Ta'ala and all of you, the second International Conference on Chemical Engineering and Applied Science is officially open. Have a good conference. Thank you very much. Wassalamualaikum warahmatullahi wabarakatuh.
Thank you for all the welcoming speakers and attendees at today's conference. Now let's move on to the keynote speaker session. Keynote speakers are Professor Hidefumi Yoshi from Satsuna University, Japan, as the first keynote speaker, and Associate Professor Jaka Sunarso from Swinburne University of Technology, Malaysia, as the second keynote speakers. In this session, we will be leading by Dr. Engineering Vita Paramita. Please extend a warm welcome to the moderator, but let me first read the curriculum vitae. Dr. Engineering Vita Paramita graduated from Tottori University of Japan and Diponegoro University, and she is now Associate Professor in Department of Chemical Engineering Vocational School of Diponegoro University, and her main research is about encapsulation of flavor and functional compounds by spray drying. To Dr. Engineering Vita Paramita, from whom the time has been allowed.
Good morning, dear participants of IKEAS 2021. We are pleased to have you joining our keynote speaker session. My name is Vita Paramita, and I'm going to guide this inspiring session. Today, we will have Professor Hidefumi Yoshi from Setsunan University, Japan, and Associate Professor Jaka Sunarso from Swinburne University of Technology, Malaysia. On behalf of the organizers, each speaker will deliver their presentation for 45 minutes and following by the 15 minutes of discussion. Excellencies, honorable speakers, and greeting for all participants. We have the first presenter here with us, Professor Hidefumi Yoshi. Before starting the presentation, I would like to share his short biography. Professor Yoshi is a professor of food engineering laboratory in the Department of Food Science and Human Nutrition at Setsunan University in Osaka, Japan. And he is also the emeritus professor of Kagawa University in Takamatsu, Japan. His main research is the encapsulation of functional food compounds by spray drying, kneading, and molecular encapsulation with cyclodextrin and the characterization of the encapsulated powder. He has over 37 years of education and research experiences in food engineering. He has awarded Scientific Achievement Award in Tottori University, Research Incentive Award in Japan Society for Food Engineering, and Arun S. Majumdar Medal for Outstanding Mentorship and Sustained Excellence in Drying Research. Professor Yoshi also active as editorial board of some reputable journal and administration officer of International Exchange Committee in Japan Society of Food Engineering. In this awesome opportunity, he will present the applied research entitled Development of a New Functional Packaging using 1-methylcyclopropene or 1-MCP in alpha-cyclodextrin. I'd like cordially invite Professor Yoshi. Please, time for you.
Yeah, just a moment, please. And could you see my
Yes.
slide?
Yes, we can see the slide, Professor.
Yeah.
Yes.
So it is a great honor to be able to speak to you today. Before I start, I would like to thank this meeting organizer for inviting me to speak today. So I'd like to talk about the encapsulation of functional compound in cyclodextrin. So especially my title is the development of a new functional packaging using 1-methylcyclopropene, we call 1-MCP in alpha-cyclodextrin. So first, I'd like to introduce the cyclodextrin. Oh, just here is the today's introducing content of my presentation. First, I want to introduce the cyclodextrin. Second, water is essential for the inclusion complex formation. Third, flavor release rate from cyclodextrin complex depend on the moisture concentration. And then I want to introduce the 1-methylcyclopropene, and then collapse of 1-methylcyclopropene alpha-CD powder, and finally the 1-MCP treatment of upper storage. This is these my presentation topics. So first, I want to introduce the cyclodextrin. So this slide shows the structure and physical properties of cyclodextrins. Cyclodextrins are non-reducing chiral cyclic oligosaccharide in which the glucopyranose units are linked alpha-1,4 glycosylically into a ring. Depending on the number of the glucopyranose units and then size of the ring, a distinction is made between alpha, beta, and gamma cyclodextrin. So the alpha keys, the cavity diameter is about 4.5, beta cyclodextrin 7.0, gamma cyclodextrin have cavity diameter 8.5. This cavity could be included as some guest compound. And then solubility is the beta cyclodextrin lower than the alpha and gamma cyclodextrins. The cavity of cyclodextrins hydrophobic due to the hydroxyl group arrangement, and then outer rims are hydrophilic. So inside the cavity is hydrophobic. So this slide shows the product example using cyclodextrins in Japan. The supplement of coenzyme Q10 is a vitamin-like compound and an important substance involved in the human energy production. Cyclodextrins are used to prompt the absorption of this substance into the body. Next to it, this is the raw wasabi. The purpose is to stabilization of the allyl isocyanate. Another product is the green tea. So this green tea contains the higher concentration of the catechin included in cyclodextrin. Another purpose is the inclusion of the odor, and the bath smell compound could be included in the cyclodextrins. The purpose is the deodorant. So that we can see that a lot of the cyclodextrin products in food industry. So I want to show the detail of the coenzyme Q10 supplement. This slide shows non-micelle formation of the coenzyme Q10 using gamma cyclodextrin and the potassium glyceridate. Coenzyme Q10 has been reported to have a wide range of positive therapeutic effect on human health as a nutraceutical ingredient in supplement and health food. The solubility of coenzyme Q10 in water is extremely low, resulting in low bioavailability. When coenzyme Q10 mixed in water, it's float as the agglomerate as shown in the left figure. When gamma cyclodextrin is added into the dish system, we can get the slurry solution. And then we add the glycerol, we can get the coenzyme Q10 mixture. So this phenomenon suggests the interaction and the replacement reaction of surfactant to coenzyme Q10 and gamma cyclodextrin inclusion complex might form the micelle formation of coenzyme Q10 and surfactant. So this is the application of the coenzyme Q10 to the skin health. So high coenzyme Q10 uptake by human epidermis cells was observed when the solution prepared from coenzyme Q10 gamma cyclodextrin complex with glycerol was applied. In comparison, other standard cosmetic formulations using liposome and the fatty oil-based emulsifier show the negligible absorption to the skin. It was shown the high uptake of coenzyme Q10 epidermis in the coenzyme Q10 gamma CD plus glycerol solution compared with other coenzyme Q10. Cyclodextrin using in food engineering field as a stabilizer, encapsulant, and powdered material. Cavity of the cyclodextrins are hydrophobic property to form the inclusion complex. So the water molecules are essential in association and inclusion processes as shown in this slide. we would like to consider how many water molecules are needed for the inclusion. In the inclusion process, water is essential for the inclusion to recognize the hydrophobic cavity in cyclodextrin. The bottom of this slide shows a molecular model in the inclusion of the flavor compound dilemonan into alpha-cyclodextrin. In the inclusion of the dilemonan to alpha-CD, the replacement of the water molecules and the gas molecules in cyclodextrin cavity occurs. What is the minimum water molecules required for the inclusion? So we investigate this problem using the microarchaeas method. This is the microarchaeas method. Dry cyclodextrin, add the dilemonan, the solvent, and add some amount of the water, we mixing and incubation after we could get the dried powder. And then measure the inclusion of dilemonan by the EC. This microarchaeas method requires the inclusion process can be proceeded in a liquid gas such as dilemonan. Flavor inclusion process in an aqueous solution could be described the reaction model in this slide. This is the autocatalytic reaction of water, where CD gas denote the inclusion complex and NH2O on the right are the water molecules released from the CD cavity during the inclusion process. Figure shows formulation of the inclusion complex between dilemonan and cyclodextrin with various water content. We could get this kind of the data. About the 20 molecules of water, we could get the full inclusion. By this data, we could get the minimum water molecules for the inclusion. The reaction scheme implied the inclusion process is autocatalyzed by the water. By this autocatalytic inclusion process with water, molar ratio of the included dilemonan to CD could be expressed that this equation. R is the inclusion ratio of the dilemonan to the cyclodextrin. R max is the maximum inclusion. W is the number of the water molecules. When we solverize this equation by this condition, we can get the equation 1. So by using the equation 1, we can correlate the inclusion behavior. This slide shows the kinetic analysis using autocatalytic inclusion. The solid line shows the above this equation 1. So by using this solid line, we could get the minimum water for the inclusion. So these results suggest the inclusion process could be simulated with autocatalytic reaction model of the water by using the intercept of this 0.5 slope at the inflection point of R at 0.5. The minimum water content required for inclusion W minimum can be calculated as follows. The inclusion complexes were barely formed at their water content with all the cyclodextrins. The inclusion ratio increased gradually with the increase of the water content, but over specific moisture content, which is roughly 2, 4, 10 for alpha, beta, and gamma cyclodextrin respectively. So by using this equation, we could get the minimum number of the water molecules needed for the formation of inclusion complexes. Alpha case 4.45 and beta 7.43, gamma and 9.93. When we think about the release of the limonin, we can estimate released water molecules 4, 7, 8. We could get the very resembled values. So for the inclusion, the water is essential. The minimum number is about this number. Next, I want to talk about the flavor release from the inclusion complex powder. This is the model of the flavor for the experiment. Aryl isothiocyanate, D-limonene, and hinoxidil. By kneading method, we could get the inclusion complex powder. So inclusion ratio is about depend on the cyclodextrin and of the flavor compound. By using the kneading method, we could get the included powder of cyclodextrin and the flavor. And then using this dried flavor compound of cyclodextrin, put in this instrument, we measure the release of the flavor compound from cyclodextrin powder at constant temperature and the constant humidity condition. So inclusion complex powder was stored in glass bottle. This glass bottle, the temperature and the humidity controlled air flowed into this vessel. At fixed time intervals, the glass bottle was removed from the constant temperature bath, and the retention of the flavor in the powder was measured by CDC. This is the experimental result for the release of the different flavors included in beta-cyclodextrin. Y-axis is the retention of the flavor, and X-axis the storage time. This is the condition temperature is 50 degrees Celsius. Hinoxidil exhibit and the extended release are good controlled release properties, even in higher relative humidity at 90%. Aryl isothiocyanate shows the rapid release, and D-limonene has moderate release rate. So next slide showed the release of the D-limonene included in different cyclodextrin, alpha cyclodextrin, beta cyclodextrin, gamma cyclodextrin. D-limonene included in alpha cyclodextrin behaves a good controlled release properties compared to the beta and gamma cyclodextrins. So this slide shows the effect of environmental humidity and temperature on the D-limonene release behavior from the inclusion complex of D-limonene in beta-cyclodextrin. Left figure is affect humidity. Right figure is effect of the temperature. The retention of the D-limonene, so release behavior depend on the environmental humidity. And then also the release behavior, release rate depend on the environmental temperature. As the relative humidity was increased, the release of the D-limonene was greatly accelerated, particularly between the 60 to 75 relative humidity. The effect of the relative humidity on the release was more pronounced than the temperature. This suggests that the release of the D-limonene was closely related to the presence of the water molecules surrounding the powder. So we analyzed those release behavior by using the Abraham equation. So the analysis of the flavor release from the inclusion complex powder is complex and difficult, since it is a phenomenon in which various events, such as the inclusion, diffusion, adsorption, and replacement between cyclodextrin's flavor and water molecules. We applied Abraham equation or Weibull equation to the analysis of the flavor release. This is the Abraham equation. R is the retention of the flavor, K is the release rate constant, N is the parameter of the release mechanism. When we use this equation to analyze the flavor release, we can get the release rate constant. So N means the parameter of the release mechanism. So we can analyze the flavor release behavior of from the cyclodextrin inclusion complex powder. When we applied this Abraham equation to the release of the flavor compound, we can get the release rate constant. This is one example of the plot. This is the analysis. This slide shows the analysis of the release by Abraham equation. X-axis natural logarithm of t. Y-axis is natural logarithm minus natural logarithm of the inclusion ratio. We can get the straight line from this line. We can get the mechanism number of the N, and then also get the release rate constant. For beta cyclodextrin case, N equals 0.67. Gamma and the alpha cyclodextrin case, N equals about 0.3. By using the Abraham equation, we can get the release rate constant. When we plot of the release rate constant against the water vapor concentration, we can get the good correlation. These slides show the effect of the moisture concentration on the D-limonene release behavior from the inclusion complex of the D-limonene or allyl-thioisocyanate. Left figure case allyl-thioisocyanate. Right figure for D-limonene So the gamma cyclodextrin and beta cyclodextrin could get the higher release rate constant. And the alpha cyclodextrin case, lower release rate constant than the gamma and beta. The limonene case, the dependence of the water vapor concentration of the release rate constant, we can get the three line, gamma and beta and alpha cyclodextrins. So this slide shows the release rate constant depend on the environment water vapor concentration. So we check the effect of the humidity on the limonene release from the inclusion complex of the beta cyclodextrin. This figure shows effect of the repeated stepwise relative humidity on the release flux of the limonene in beta cyclodextrin. Blue line and point show the humidity change in the chamber, and the red line and the point show the limonene flux. So we could control the flavor release from the inclusion complex in the environmental humidity. So this phenomenon could apply the fruit package to control the freshness of the fruits and vegetables. So next slide showed the development. I'd like to talk about the development of the new functional packaging using 1-methyl cyclopropane in alpha cyclodextrins. First, I want to introduce the 1-methyl cyclopropane. So what is a 1-methyl cyclopropane? So 1-methyl cyclopropane is an echelon inhibitor in plant physiology. So 1-methyl cyclopropane could delay the ripening, senescence, color change, and softening in fruits and vegetables. This compound very effective at low concentration, ppm or ppb level. But this gas have explosive properties above concentration is 1%. Therefore, in commercially, the 1-MCP included in alpha cyclodextrin. So the commercially, we use the cyclodextrin powder, inclusion complex powder. Next slide shows the climatic fruits. Fruits are generally divided into two types. One that respond to the echelon, one does not. So a fruits whose ripening is prompted in response to the echelon is called climatic fruits. These photos show the climatic fruits. So echelon is a plant growth hormone that is active ripening. So echelon is a phytohormone that has always been considered determinate to the storage of the fruits. Hence, mitigation of the echelon effect is of great interest, especially for the perishable produce. So the echelon effect is the decreasing of the quality of the fruits, fresh softening in fruits, shelf color change, short life of the fruits. So that we have to inhibit the ethylene effect of the fruits. So we applied 1-methyl cyclopropane is the ethylene inhibitor of the fruits. So ethylene has been also reported as the major factor in ripening process of the fruits. This slide shows the mechanism of the 1-MCP action. So yellow, this is the ethylene receptor, blue is the ethylene. So binding the ethylene receptor, ethylene bind the ethylene receptor, and it occurs ripening. So the fresh softening in fruits, self-color change includes a flavor component. When we use the inhibitor of the 1-MCP, so the ethylene could not bind the ethylene receptor. So when 1-MCP bind the ethylene receptor, ethylene could not bind the ethylene receptor. The ripening and the senescence are inhibited. So that we could stop the ripening by using the 1-MCP. This is an example of the 1-methyl cyclopropane applied, 1-MCP applied for the watermelons. For treated watermelon, so that we could see the very soft part. But treatment of the 1-MCP, we could get the fresh watermelon. And this photo is a treatment of the carnation of 1-MCP, no treatment, 1-MCP treatment, and the treatment of the STS. So that these photos shows the effectiveness of 1-MCP on maintaining of the freshness of the carnation. And then also, we want to show the effectiveness of the 1-methyl cyclopropane on the tomato colors. So the 1-MCP inhibited the tomato ripening after 18 days of 1-MCP treatment. This is a control, and 5 milligrams of the inclusion complex powder, 15 milligrams of the inclusion complex powder, 30 milligrams. So 1-MCP inclusion complex powder could delay the color change tomato. So this is the Arianto and our data. So first, I'd like to show the synthesis method of the 1-MCP and get the 1-MCP inclusion complex powder. This reaction is a 1-MCP synthesis. So first, we prepare the lithium D is a propylamide and the 3-chloro-2-methyl-propane. We could get the lithium salt of 1-MCP. This is the at room temperature reaction. This is the lithium salt of the 1-MCP. We put in the lithium salt of the 1-MCP in the water, in the closed vessel. 1-MCP gas evaporated, and then gas moved to the another bottle contain the alpha cyclodextrin solution. So in this bottle, we could get the 1-CP alpha cyclodextrin inclusion complex powder in the gas absorption of 1-CP into the alpha cyclodextrin solution. The 1-CP alpha CD inclusion complex is a crystal. In this case, and we get the molar ratio is 0.6, about 7. This is the photo of the inclusion complex crystal. This slide shows the gas absorption of 1-CP gas in alpha cyclodextrin solution. Y-axis is the 1-CP retention in headspace of the encapsulation system. X-axis is the encapsulation time. The solid line were calculated line by the using Abram equation. The encapsulation rate constant was obtained with the fitting of the gas absorption behavior. We could get the release gas absorption rate constant. So this apparent encapsulation rate constant, gas absorption rate constant, depend on the alpha CD concentration. The apparent encapsulation rate constant could be obtained by using mechanism number 0.65. This value indicates the 1-CP gas absorption into the cyclodextrin, alpha cyclodextrin slurry solution is the Schulze first order chemical absorption, which is estimated the film theory. So next slide shows the release characteristics of the 1-CP from the inclusion complex at 25 and various relative humidity at 50 degrees Celsius, and also the various relative humidity. So I would like to explain the physical characteristics 1-CP release from the inclusion complex powder. This figure shows 1-CP release from the inclusion complex powder at 25 and 50 degrees Celsius, and for the various humidity. At 25 degrees Celsius, 1-CP retention dropped and the release 1-CP stopped after the initial date. Also, at 50 degrees Celsius, 1-CP retention dropped, gradually decreased. This sudden stop of 1-CP release is due to the aggregation of 1-CP powder. So that these photos, this is the same photographs of the 1-CP alpha CD crystal inclusion complex powder. This is the initial crystal. After 10 days storage at 50 degrees Celsius, the crystal became the aggregated powder. This aggregation of the inclusion complex powder inhibited continuous 1-CP release. Another experiment. This slide shows the release characteristics of 1-CP from inclusion complex powder. using DVS PTR mass. Red dotted point show the relative humidity at the environment. The blue line showed the YMCP release. YMCP release was drastically retarded at the 80% of the humidity, relative humidity, presumably owing to the agglomeration that reduced the specific surface area of the inclusion complex particles. So YMCP alpha CD inclusion complex presumably absorbed moisture at high relative humidity, resulting in the collapse of the crystalline structure and subsequent release of the YMCP. At the 90% relative humidity, the release of YMCP may probably be facilitated by partial dissolution of the inclusion complex particles. So that this slide shows the same photographs of the inclusion complex powder for the various relative humidity. Agglomeration of the inclusion complex particles plausibly increase the diffusion distance of YMCP to the surface of the particles. Thus, the retarded its release high relative its release. So high relative humidity increased the mobility of the molecules, which resulted in the loss of the crystallinity and contributed to the release of the YMCP. Morphological alternation of the inclusion complex particles shown by SEM is in good agreement with both the YMCP release profiles and the weight change. So next, I will talk about the upper storage using YMCP included in the alpha cyclodextrin. So we have to inhibit the sudden release stop. So that we have to inhibit the collapse of the inclusion complex powder. Therefore, we use the YMCP coated paper to store the apple. Using the shellac solution, YMCP inclusion complex powder, make the YMCP inclusion powder in the shellac solution in the slurry state, and then put on the white paper. We could get the YMCP coated paper after drying of the after evaporating the ethanol solution. So this is the YMCP coated paper, same of the YMCP coated paper. So we use this YMCP coated paper to store the apple in the package. Main issues during the shipping of the apple: ethylene receptors of the fruits are resting at cold temperature. When storage of the temperature of the fruits change from the cold temperature to hot temperature, from about the 4 degrees of Celsius to became the 20 degrees of Celsius, ethylene receptor appears on the surface. So ethylene receptor come into existence on the fruit surface, and fruits became quickly ripening. So we want to inhibit this ripening at the temperature change. This is a polystyrene box. We put in the 40 apples into the box. This is the YMCP coated paper. So we applied 0.550 milligram YMCP and then another compound. First, we keep the 4 degrees of Celsius 15 days and then change the 20 degrees of Celsius. And the first analysis after 15 days at the 20 degrees Celsius, and then also the continuous storage, the more 14 days. This point is the first analysis of the apple. This point is the second analysis of the apple. So this is the storage conditions and the apple, and this is YMCP coated paper. In this case, we use the small piece of the white paper, YMCP coated paper. This slide shows ethylene concentration during the storage. Black side is the 4 degrees of Celsius. White part is the 50 of temperature, the 20 degrees of Celsius. So the control case, after the temperature change, the ethylene concentration increase in the box. The ethylene concentration depends on the YMCP powder. The 50 milligram of the powder, we can inhibit the ethylene formation. This is the result of the ethylene production rate of apples in the first analysis. So first analysis is this point. After 15 days storage at 12 degrees of Celsius. So the control case, ethylene formation about 45. But we use the inclusion complex, 10 milligram, 30 milligram, 50 milligram. We could inhibit the ethylene formation. This is the ethylene production rate of apples in the second analysis. Second analysis case. So the 50 milligram case, ethylene formation could be inhibited a little bit. So the control case 29, about 30, and 50 milligram, and about the ethylene formation rate is 13. So in this case, so ethylene production rate of apples could be inhibited by using the YMCP coated paper at first analysis term. This slide shows firmness of the apples. This is control. This is the 50. So the firmness is a little bit higher than the YMCP coated paper. This is the kind of the apple is the Fuji case. This slide shows the titral acidity of the apples. Also the titral acidity a little bit higher than the control case. The first analysis and second analysis case. So and then we applied the Fuji apple and the Orange apples, and this year, this January. So the Orange apple, the ethylene formation concentration is very high. Fuji apple case is ethylene formation after change of temperature change, the maximum about 60 ppm. But Orange apple, the ethylene concentration in the box about higher than the 400. When we applied the YMCP coated paper to inhibit the ethylene formation, we could inhibit the ethylene formation of the Fuji and the Orange apple. This slide shows the effect of the YMCP coated paper without the 2-methyl-butanol. Because when we inhibit the ethylene formation, when we inhibit the ethylene formation and inhibit the ripening, we could not get the good smell. So ripening formed the good smell, good flavor. But when we inhibit the ripening, we could get the good smell. This is the one problem in the using of the YMCP. So this is the Fuji apple case. It's first analysis and second analysis, another experiment. Also, we can inhibit the ethylene formation. This is the damaged apples ratio. The control case is about the 0.5. But the YMCP is the rate of the damaged apple is lower than this 0.5. Orange case, also we could get the good results. So this is a control, please see the blue bar. Control case, the ethylene formation 140, but we applied the YMCP 100 milligram and we couldn't see the ethylene formation. Firmness, we could apply, we could improve the firmness by using the YMCP. Also, this titration acidity also damaged the apple. So that we could apply the YMCP coated paper to store the apple. We could inhibit the ripening by using the YMCP coated paper. So in the release of the behavior of YMCP powder, environment moisture concentration are very important to control the release of the gas compound in the CD cavity. So the
Excuse me,
environment,
Sensei,
yeah,
the remaining time is 10 minutes again. Thank
Yeah.
you.
thank you. Almost the finish, and this moisture water is very important. So in conclusion, water molecules are essential for the inclusion and the release of the gas compound in cyclodextrin. So the Abraham equation could be used to the analysis of the flavor release from the inclusion complex powder. So the YMCP coated paper treatment was effective to inhibit the ethylene production rate during the apple storage time. So finally, the acknowledgement to the many PhD students, the yellow part student, yellow part doctor investigate the cyclodextrin's topics, and the other part is the investigate the encapsulation of the functional compound in by spread drying. And then also the students, many students from the Kagawa University, Totoro University, and the Agroscope division in France, and the Charles University investigate those topics. And then also we cooperated the BDD in Finland. So then finally in this book, so that you can see my presentation topics. So the last month, we could publish this book, Functionality of the Cyclodextrin and Expression for Food. So thank you for your attention. Yeah, thank you. We finished the presentation.
Professor Yosi, for the insightful presentation session. Any participants? Do you have any question to the Professor Yosi? Okay, while with some question, Professor Yosi, I would like to ask about the phenomenon of the release rate in the cyclodextrin. As your explanation before, the release of different flavors in cyclodextrin provided different character also
Yeah,
regarding to the type of cyclodextrin.
yes,
However, the alpha CD is the smaller capacity of cyclodextrin, but it behaves a good control release properties compared to the beta and gamma CD, even though gamma CD provide better inclusion complex. So, Professor, would you like to give us enlightenment about this phenomenon? Thank you.
so the alpha cyclodextrin could be encapsulated, for example, this kind of the small molecules. So the release behavior depend on the cyclodextrin and then also the structure of the flavor. So, for example, in the beta cyclodextrin case, at high humidity, hinoxidil, we could keep the retention of the hinoxidil at high humidity, but allyl could not keep in the cyclodextrin. So that when we want to use some release to kill the bacteria or by using the flavor to the fresh storage, so we have to select the cyclodextrins and then flavor compound. So the YMCP case, YMCP is a very small molecules, and then alpha cyclodextrin cavity is a very small. Therefore, we could control the YMCP release in the at the temperature change at 20 degrees Celsius. In the packet, relative humidity in the upper package, almost the 90% relative humidity. Therefore, we could see the release of the YMCP in the package at the temperature step change. It's okay?
Yes, it's clear. Thank you, Sensei. And also, explained that the storage temperature will affect the release rate of the gas. Yeah, this is very interesting presentation, I think. So the different type of gas will affect the release mechanism and also affect the inclusion reaction itself. I think we have enough presentation and discussion, and I'm going to point out the first session of the keynote speaker. Professor Yosi have explained that the inclusion complex powder of 1 MCP in cities was effective to inhibit ethylene production rate during the apple storage time. This inclusion reaction and its release rate of gas compound in cyclodextrins were mainly affected by the water molecules, and the release of main component well approached by the Aframi equations. I'd like to express my gratitude to Professor Yosi for his fruitful speech. It gave us many benefits of applied science in food engineering. And before I'm closing the first keynote session, the organizers would like to deliver a certificate as a keynote speaker by displaying it online. Please. Yeah, this is our appreciation for Professor Hidayat. Very much, Professor Yosi.
Thank you. Thank you.
Well, our distinguished participants, we are coming to the next speaker. The second speaker is Associate Professor Jaka Sunarso from Swinburne University of Technology, Malaysia. He will share his research experience entitled Simulation Study of Oxygen Permeation in LCF Argentum Hollow Fiber Membrane at different flow configuration. Before we are going to have our next speaker, I wish for sharing his short biography. Dr. Jaka Sunarso is currently an associate professor in the Faculty of Engineering, Computing, and Science, and also the director of the research from the University of Queensland in Australia in 2006 and 2010, respectively. He was awarded an Alfred Deakin Postdoctoral Research Fellowship at Deakin University, Australia, and then secured a Banting Fellowship at the University of Waterloo in Canada. His main research interests are batteries, fuel cells, membranes, and biomass conversion to fuels and value-added products. Dr. Jaka has published more than 180 journal articles in chemical engineering and material science field, with total citation more than 8,000 and an H index reach of 45. He has actively supervised 11 PhD and 7 master students. In this exciting occasion, I'd like to sincerely invite Dr. Jaka for presenting his study. Please, the time is yours.
Okay, Thank you. Before I start speaking, my sound is clear and the screen is shared properly that everybody can see?
Yes, it sound clear. Thank you.
Okay, thank you so much, everybody, and have a good morning. I would like to thank organizing committee, in particular Dr. Hermawan, and also the rector and the top management of the Universitas Diponegoro for inviting me to this conference. So today I would like to speak about one of my project. It's about the progressions from the experimental to the simulation, in particular the use of the Tanley model for perovskite silver oxygen selective mixed ionic electronic hollow fiber membranes. So the name that I put in here is basically the people that are contributing to this particular work. Okay, so this I'll go through the through the chronological and also a little bit on the background and also how these collaborative projects lay out. So the outline for this morning key talk is first I will talk a little bit about the research group and also the collaborative work which universities are involved in this collaborative work. And then to set a setting for this work, then I will talk a little bit about the background of the research work that I present in here. And then I'll go a little bit into the hollow fiber membrane because the experimental and the modeling of this particular research work that I present in here is based on the hollow fiber membrane geometry. And then we will go a little bit into the technical, into the simulation study, into the technical insights of each of the configurations that our group study in here, followed by the conclusion and then the acknowledgements. If there is anything that is not clear during the presentation, please don't hesitate to stop me or drop me any questions later on also. Okay. So first I will talk about the background of this project and a little bit into the Swinburne University Technology Sarawak campus where I'm at the moment. Okay. So this work is actually a collaborative or a joint project between 4 universities. So the university that I'm in is basically the Swinburne University of Technology Sarawak campus. And this is a snapshot of our campus in Sarawak. So this is a branch campus of the Swinburne University of Technology in Houghton, Melbourne. I think was established in 2000 as a joint venture between the Sarawak state government own about 75% of the share, with the other 25% is being owned by the Swinburne Houghton. Okay, so
Excuse me, Dr. Jaka, is
Yes.
there any slide that you need to share with us?
is it not out? The slide is not out.
Yes, it
Oh, wait
is
a
not
second.
out yet.
Let me check. I think I have a little bit of share screen. Okay, so this one, isn't it? Okay, so now everybody can see this one, this slide as well.
Yes, okay, thank you.
Oh, sorry for that. I missed, so because I also not very familiar with the Zoom. So let me go into this outline already, and then this is about us. So this is where I am basically at the moment. Okay, so the one on this right hand side in here is let me go back again. This research work is basically a joint project between 4 institutions, and the institutions where I'm in is Swinburne University of Technology Sarawak campus, and this is the snapshots of the campus in Kuching, Sarawak. So it's basically nearby Pontianak. And then this, like I told before, the Swinburne University of Technology Sarawak campus is a joint venture between, it's a branch campus of the Swinburne University of Technology in Houghton. And it's a joint venture between Sarawak state government, which own about 75% of the share, with the other 25% of the share comes from the Swinburne University in Houghton. And also in this project, we are also working with the Curtin University, especially the group of Prof. Xiaomin Liu, and also with another group in the Shantung University of Technology, and then also in Beijing University of Chemical Technology. So like I said before, the Swinburne University of Technology Sarawak campus, this is giving a bit of the snapshots, and this is an aerial view if we use a drone to capture this one. And this one is a plenary lecture hall. This here a picture of our students in the lab, and this one is in the class. So this one was established in 2000. It has about 3,500 students, but now with the current pandemic affecting, then I think we will have a bit of drop in the number of the students, especially in the international students, because the border is closed. About 25% is the international students, and then we have two faculties: business, design and arts, engineering, computing and science, plus the School of Research and the School of the Foundation Studies. And these are our Swinburne Sarawak Research ecosystems, and the map in the right-hand side in here represents the global network that we have along in the world. For example, we have a lot of collaborators in the America, and then some in the Europe, and then also in South America as well, and mostly are concentrated in Asia. And these are the entities. So we have a School of Research that basically serve as our research office, and then we have 4 research centers, and then faculties. So our staff is our researchers are basically our staff, and we are affiliated with the research centers in here. We also have an entity for the research-led services in terms of the short courses and also the innovation and the commercializations. So our chemical engineering program in Swinburne University of Technology Sarawak campus is a bit unique in terms that it doesn't have the counterpart in Swinburne University of Technology Hawthorne, because we have the local market in here, but Swinburne University of Technology Hawthorne, they don't really have the market offer in Melbourne, because they have to compete with the University of Melbourne and also with the RMIT, and also with the Monash University that basically forms the largest programs of chemical engineering in Melbourne. So our small chemical engineering program in here launched in Q3 2012, and with the first batch of the graduates, it produced on 2016. So it has run about 9 years. Okay, and then the graduates will get the degree from the Swinburne Hawthorne, and it's approved by the MOHE in 2012, and our accreditation is coming from the Malaysian Engineering Accreditation Council. These are an overview of our curriculum in our chemical engineering program. So the students start on getting the core chemical engineering program on the year 2. Basically, the introduction to chemical engineering here is the same with the mass and energy balance that we get in Indonesia, and then we also have a fluid mechanics, and then transport phenomena, process modeling, and the bar in here is put in here because I'm teaching this process modeling, and then we get in 4 year is a process plan design, where the same in Indonesia that we have that design pabrik kimia. And we have 2 semesters of the final year research project, and the students normally they can consider if they want to do a postgrad or in terms of the master or a PhD after they do this final year research project. So our research area in chemical engineering program in Swinburne University of Technology Sarawak campus, we have several key areas. One is done in collaborations with the main campus is on the energy storage. It's basically a graphene-based supercapacitor. The one that form the backbone of what I have been trained is the ceramic membranes for clean coal combustion and H2 production. So this is forming the main research work that I will present later on. Okay, and then another colleagues, or I think about 2 or 3 colleagues of mine, they are also doing an energy planning using a pinch analysis in here as well. And then also another hot area that fits within the local context of the Malaysia and Indonesia is how do we convert the waste surrounding us, the oil palm biomass particularly. So a major part of interest in chemical engineering program is also using the thermochemical processes, such as the dry wet torrefactions, the wet torrefaction, pyrolysis, gasifications to convert the oil palm biomass waste into chemicals and value-added products. Okay, so this is actually almost the same. So it's also oil palm biomass conversions to fuel and energy, and it's the slides in here is basically showing the same variations. It's just a little bit details. Okay, so now I will go into the backgrounds of the oxygen ionic separation membrane technology before I go into the technical parts of that thing. So oxygen, why oxygen is important? Because oxygen is a very highly sought chemicals in many industries, in healthcare, chemical, energy, in everything. So sometimes we also need to use, I think, a purified oxygen. Sometimes you need to use it for treatment of the COVID-19 patient, for example, but that will not be the only use for this oxygen. Oxygen is also used in a lot of chemical industries. So the conventional route or the conventional technology to use this to get the oxygen is basically can be pinpointed into two routes. The first one is the cryogenic separation. So this one is involving a distillation process. So and then the other one is basically a pressure swing adsorption. So in here is we are using an adsorbent. So in in cryogenic separation, what you do is basically you need to lower down the temperature of the gases, because normally the source of this oxygen is basically air containing about 79% of nitrogen and 21% of the oxygen. So when you cool down to a very low temperature, then you will be able to make it into a gases, and then that based on the boiling points difference, then you can then recover the nitrogen and the oxygen. So these are the conventional route, and where you can produce a very high purity of oxygens. But the downside of this is that it requires not only the high capital cost, but also the operating cost as well. The pressure swing adsorption, on the other hand, is probably not as energy intensive as the cryogenic separations, but the downside of this is, of course, you need to have a selective material because you are relying on the adsorption principle, and adsorption is basically depending on how much is the selectivity of oxygen or nitrogen that can be attached to that particular the surface of that particular adsorbents. The downside of these things is that it cannot reach a very high purity as in the cryogenic separation. Okay, so now what we are talking about in here is a new technology. Is called it's basically a part of the membrane technology, but bear in mind that in membrane technology you have a different types of the technology. The first type of the technology will be the porous membrane. So you know that the gases basically they have a different size. So we call it a different kinetic diameters. So if you can have a porous membrane with a tailored size of the aperture, such that the aperture lies in between the size of the gas component that you want to separate with those that the gas that you want and the gas that you don't want, then ideally you can separate you can achieve a separation. But this particular technology is a totally different technology. This particular technology is not depending on that porous membrane or the aperture size to achieve the separation. Rather, this membrane is a special type of the membrane because it's called a dense mixed ionic electronic conducting membrane. Dense meaning that we don't have any pores at all in the membrane, but rather the transport of the oxygen will go through the lattice of the membrane, meaning that this relies on the formations of the oxygen vacancies within the highly ordered perovskite membrane. Because when you heat up to the high temperature of above 700 degrees Celsius, then you basically creating an oxygen vacancy in your lattice. Okay, so okay, bear in mind that the perovskite structure has this kind of a structure. So where it basically consists of the A, B, and O. Okay, it has a structure of AbO3, where the A side cation is normally coming from this particular metal components, if not lanthanum or 2A, and the B side cation coming from the transition metal element, and then the oxygen is basically sits where they are in there. Now, the thing that I have to bear in mind in here is that there is a different size of the A, B, and then the O, as you can see in here. And then the transition metal element is put into the B side in here to allow for the electron conductivity to occur in the membrane, because without the electronic conductivity form in your compound, that the membrane technology will not be called as a mixed ionic electronic membrane technology. Okay, so that membrane technology is important because as the oxygen goes through one side, from the feed to the permeate side, then the electron has to go from the permeate side to the feed side to compensate for that charge change. Okay, so these are the schematic of the process itself. Okay, so what happened is, of course, you need to create a difference in terms of the oxygen partial pressure difference. You imagine that this side is the feed side, the other side is the permeate side. Okay, so if you want to have a transport from one side to the other side, then you have to have a driving force. So the driving force can be created. So for example, by you can probably expose the feed side into the air. So this will have the oxygen partial pressure of 0.21. And the permeate side in here, you can vacuum, you can create a vacuum, or you can basically pass sweep gas. It can be a water, or it can be argon, or anything again that can be replaced easily, that can be recovered easily later on. Okay, so what happened essentially is that you have 3 steps. The first one is when the oxygen molecules is in contact with the surface of the feed side in the membrane here, then there will be a surface exchange reaction. And then there will be a bulk diffusion of the oxygen ions in here. Okay, like I mentioned, the oxygen ion has to go from the feed side to the permeate side, and on the other side, it has to be compensated by the electron diffusion also from the permeate side to the feed side in here. Okay, and then lastly, they will have a surface exchange reaction to convert back the oxygen ions into molecules. The details on this one can be found in our recently published publications in Advanced Functional Materials, where we have collaborations with the German groups and the Chinese group as well. So you will ask me now, why this MIEC membrane is very important? Because the things that we have to convince our students before they want to go into research is why our research is important. So that's the same way with the previous session where we talk about the importance of the food packaging. So in here, instead I start first. So now this MIEC membrane, as I showed in the previous slide, it's only allowed at the higher temperature. But remember that when we are burning a coal, for example, then we can get the energy from the coal combustion itself. So the heat can be supplied back into the membrane module. Okay, so in essence, the energy can be integrated directly from that coal power plants. And then when we one of the technology that we can use for the future for the clean coal combustion is basically burning the coal with the concentrated oxygen, so that we can get a highly concentrated CO2. So in this way, then the CO2 will be, if the CO2 is available in a very high concentrations, then it will create it will make the process simple later on if we want to do a carbon capture for the CO2. So the attractiveness of this technology lies in this in the integrations with the coal power plant. Okay, because of course we cannot move directly to the hydrogen yet, so we still have to use the coal, but we have to be responsible for the future generation. So we have to care about the greenhouse gases that we emit, basically. So So how does it do this thing? So what can we do is basically we can just separate some of the CO2 and use it as our sweep gas into our membrane module. Okay, so that oxygen, that CO2 plus the oxygen can be moved back into the combustion part of this coal power plant. Okay, so in essence, we have the CO2 in here. Okay, that will be used as a sweep gas. That CO2 will be used to carry on the oxygen that will be brought into the combustion unit. And then as a result of that combustions, we will have only CO2, okay, that will come back again. And of course, in the feed side, we will be using an air, and the residue will be a pure nitrogen. Of course, this is the ideal case, but of course, there will be many other complicating cases that we will not talk about because the CO2 is reacting a lot with our membrane. So in fact, because the membrane is based, it has strong reactions with the CO2. So it's in terms of the deteriorations, then at this moment, then we have to improve the material side of this membrane. But we will not talk about that thing. We will just talk about more into the modeling of the membrane module. So now we're going to talk about the hollow fiber membrane. Okay, so the membrane that you see in this left hand side, sorry, I go back in here again. Before we go into the hollow fiber membrane, normally we will not make it in the hollow fiber membrane, but rather we will make it in this membrane, and then we test the oxygen separation, performance for this membrane using the schematic that are shown on the right hand side in here. Okay, so this will be what I will call is a fundamental study before we go into the large scale application, because we want to be sure that when we go into the hollow fiber membrane, that our material is really worth the investigation. If we don't really investigate, for example, we want to know whether this material is giving us a very high oxygen flux. Is it really stable for a very long time? Okay, so normally the practical case is we develop this membrane first before we go into the hollow fiber. This membrane that is shown in here is normally sintered at a very high temperature at above 1000 degrees Celsius, because like I said before, this membrane is not a porous membrane. This membrane is a dense membrane. So we don't rely on the selectivity of the oxygen for this particular membrane is actually 100%. But normally the problem comes from the sealing. So we have to make sure that the sealing is very tight so that no other gases or no leakage coming out. So as you can see in here is what happened is when you do the test, because the test is done at very high temperature, that you can see that the fire, the color of the fire in there is basically because you put it in the furnace. And once we decide that we have the particular membrane, so for example, in this particular area, the famous membrane is called the BSCF, is a barium 0.5, strontium 0.5, cobalt 0.8, iron 0.2, O3 minus O3. That one is a very famous composition. For a particular famous composition, for example, then people made a lot of the hollow fiber in here. This hollow fiber is created to a process called the phase inversion. So basically you are spinning a polymeric liquid mixture, a polymeric mixture in here, and then you spin it. So you pressurize this to go through this particular spin rate, and then once it gets in contact with the water on internally and externally, then it will basically coagulate. And what you have is essentially the hollow fiber in the form that we showed on top in here. Okay, so this will be called a hollow fiber precursor, or what we call is a green hollow fiber. This green hollow fiber needs to be sintered again at 1000 degrees Celsius. And when you sinter it at 1000 degrees Celsius above, I think about 1100 or 1200, depending on the compositions and the material that you made for your hollow fiber, then it will shrink, and it becomes this hollow fiber in the bottom in here. Okay, not that this hollow fiber membrane, it has a very high surface area, because imagine if you are fitting about 100 of this hollow fiber membrane into a module. Okay, and it has a very small thickness as well for this hollow fiber membrane. Okay, the thickness is in the in the order of 50 to 200 micron. And this in here is showing you how do we do the testings in the membrane in the laboratory scale. Okay, so we are putting it inside the quartz tube in here. Okay, and then feed gas can be passed on the outside, and then the permeate side will be on the external side. Okay, so this basically the one on the right hand side give you a good picture of how we do these things in the real situations. Okay, so we are normally using it in a split tube furnace. Of course, this test is only for the fundamental test again, because of course before we make the hollow fiber membrane module with a lot of membranes incorporated inside, then what we need to put in here is we need to be sure that we are investing into the correct material. So this is why we are putting in here. Okay, now I think we have given a little bit some backgrounds into the hollow fiber membrane and the disc membrane itself. And now comes a bit into the technical things that we're gonna cover today. So the oxygen permeation through the MIC hollow fiber membrane can be described using the Tunley model. Okay, it considers the forward and reverse surface exchange reaction and bulk diffusion as limiting steps of oxygen permeation. So the general form will be this form in here. So this Tunley model actually is development of the model for the disc membrane model that was developed by the Su and Thomson before. Okay, so this Tunley, they developed this model when they were in the Imperial College, I think. At that time, Tan was the postdoc of Kang Lee. So Kang Lee is a famous group of in Imperial College group. Now he is still working on this particular type of the membrane as well. As you can see in here, that this dNO2 over dL is basically defining the increment of the molar flow rate as a function of the fiber length. Okay, so as we can see for this in this form, it shows that the molar flow rate increment, okay, is depending on the oxygen partial pressure at the feed site and also oxygen partial pressure at the permeate site. Okay, and then the other constant in here is basically that we need is inner and outer radius of the hollow fiber, and then the forward and reverse surface exchange coefficient, and also the fiber length itself. So now, for the hollow fiber membrane case, note that we have a very small thickness in here. So if you can see that in the denominator, we have 3 terms in here. Okay, so the first term in here came from the the second term in here came from the surface exchange. Okay, so this one can be, if we regard it that this term is equal to 0, then it can be simplified into this term in here. Okay, so in here, what we imply basically is that we are talking about the simplifications of the case from the generalized case into the surface exchange limited case. So this particular formula in here can only work only for a case where you have a very small thickness only. Okay, so this will not work in case we utilize this membrane only, but this simplified case is a good case for our particular hollow fiber membrane in here. So now we'll go into the simulation study. In particular, we will show how do we use these particular equations in here to fit our experimental data. Okay, and then you will ask again, why do we bother to do a simulations in here? And because simulation is very important, because before we want to do a very large pilot scale or very large industrial scale applications, then we need to basically have a perspective of what we want to achieve beforehand. So sometimes the conditions in the lab, for example, we cannot really go and pressurize the feed site up to 2 atm or 3 atm, because that requires a very good sealing to be formed in the membrane, and that will be very expensive as well, right? But with simulation, simply we can project what kind of the performance that we will get at the conditions that not really attainable in lab, for example. Okay, so it's very useful that it enables a parametric study to guide the future membrane design and the development, basically. Okay, so this basically goes hand in hand with the experimental study as well, because simulation study is sometimes really underestimated, but it really still is the hardcore of the chemical engineering. So now we in the slides that will follow in here, we're going to talk about the hollow fiber membrane. Okay, so how is it look like in the real situation? Is like this. So we have a very we have lots of the hollow fiber membrane that basically sealed on one side, and then on the other side is basically they are being sealed on the other end. Okay, if you see it on this particular diagram in here, we can depict this particular representation as consisting of this membrane module, where we put a lot of the hollow fiber membrane. So we have the shell side, and then we have the hollow fiber membrane in here. Okay, and then imagine that if we just simply put the feed air into the shell side in here, whereas the sweep gas or whatever, this one can be kept as we can use a sweep gas, for example, or we can just simply close this end and then create a vacuum on this particular side in here. So if we create a vacuum in here, then oxygen will come from here. Okay, if we create for example, we are using a water, so water can be easily separated from the oxygen by simply condensing the water, for example. Okay, even though this is not being attained in the real situations yet, but we envision that in the future that oxygen that we can use the water as or a steam as one of the candidate for the sweep gas. What is important in here to be noted is that we can have a co-current or counter current. So co-current meaning that you have a parallel directions of the flow for your shell side. In this case is air, so it will flow from this side to the other side, and then at the same time your sweep gas will flow from this side to the other side. So the flow direction, if this is parallel, then it's called co-current. But if the flow direction is different, for example, if you are passing the sweep gas from this side to the other side, which is opposite with the air to your air flow, then that will be called a counter current. Okay, so in the modeling assumptions, the thing that are important is that in the derivations of the Tanley model is that the reaction kinetics is dependent on the materials and temperature, and then the gas flow is steady, isothermal, and behaves ideally. The oxygen transport across the membrane is in the radial direction. So radial directions meaning it's spreading out from your R equals 0 to it's spreading out to your if you go in here, then it's spreading out from your I think I will go later with that. I think what you know what I meant by the radial directions. Okay, and then the O2 concentration on the varies in the axial direction. Okay, and then the pressure drop in the lumen is described by Hagen-Poiseuille equation. So this will be the simulation setting. So we put for the simulation setting in here, the inlet pressure is equal to the 2 atm. The flow rate is 300 milliliter per minute, and it refers to the standard temperature and the pressure conditions. The O2 concentration is 21%. On the vacuum side in here, if we are using a vacuum side, note that for your hollow fiber conditions in here, we have to pick between using a sweep gas or the vacuum. When you're talking about the industrial operations, then of course it will be much more productive if you are using high pressures on the feed side in here, and then either we can use a vacuum or the sweep gas in here. Okay, and we are dealing only with this particular compositions of what we call this is as an LCFAG, and then we are dealing with this particular number of the hollow fiber as well in here. And what did I want to point out in here is okay, so this is the flow configurations. Okay, the flow configurations is we are doing it the one on this top left-hand side in here is referring to the co-current configurations in here. Okay, the one on the left-hand side in here is if we are using a sweep gas. The one on the right-hand side, if we are applying a vacuum. So if we are applying a vacuum, then we just need to close this particular side in here. Okay, because all the oxygen will goes and diffuse to the side where we apply the vacuum pressure. In the counter current configurations in here, we apply the water from the different side of the feed air. Okay, and then on the other hand in here, we are basically applying the vacuum on this particular side in here. Okay, the way that we apply these different configurations will translate to the difference in the way that we are solving this particular problem. And these are the formulations that we are using. Okay, it's basically consisting of a 1D transport only, where we have an O2 balance, the nitrogen balance, and then we have this DNO2 over DL, the pressure drop. Okay, and then for vacuum mode, then we have all these assumptions in here. I would not need to go into these particular details, but for those that are interested, then I think we have published it in the materials today proceeding, and also we have recently get our work accepted in the American Institute of the Chemical Engineering Journal as well. Okay, so the kinetic parameters that we have in here is basically we are using an Arrhenius equations in here, and then we are using a multiple data points. So the thing that we get normally from the audience is that how can you be sure that your simulation basically reflect the real situation? So that's what we did in here. So we regress a large set of our experimental data that are taken at different conditions. So different conditions here meaning refer to the different conditions of the partial oxygen, partial pressure in the feed side, in the permeate side. Okay, and then also so you put in a different hollow fiber as well. If you plug in the one on the modular data on the y-axis, and then you plot the experimental data, ideally if the data is, if your simulation result is correct, then it should fall within the 45 degrees line in here, which they did. Okay, so this fitting all and this ordinary differential equation was solved using MATLAB. Everything is in MATLAB, and all the data, all the codes are provided for free as an supporting informations of the American Institute of the Chemical Engineering Journal paper that we publish. It was solved using a shooting method because it's involving a different boundary conditions. So in here basically shows the snapshot of the correlation coefficient, which is quite satisfactory. Actually, it's not satisfactory. It's actually very good because we have about 0.99, and then the sum square of the error is 0.3195. Okay, and this only applies to this particular membrane material, because for the different membrane material, then we will have a different set of the kinetic parameters as well. So now we'll go into the simulation result. And in essence, we have 5 cases that we will cover in here. The effect of the temperature is basically capturing the permeation performance versus the kinetics. And then the effect of the feed air flow rate is basically showing the permeation performance versus the oxygen available. Okay. And then the last 3 cases in here, the effect of feed air pressure, sweep gas flow rate, and the vacuum pressure is basically showing the permeation performance versus the driving force. So the first one in here is the effect of the temperature for the sweep gas mode. Okay, so this snapshot in here is given into every slide that we discuss to give an easy visualization. So as we can see, the main finding in here is that the high temperature is always leading to the better oxygen permeation performance. Because, for example, if you see in this, so for each particular line in here, it refers to the different scenario. Okay, so for this kind, if 10 fiber, the red one, the green one is referring to the 20 fibers, and then the blue one in here referring to the 50 fibers. as you can see that, of course, with the higher surface area that you put into your membrane module, then you will attain a higher performance. Okay, you will attain a higher performance, especially at the lower temperature. For example, if you're taking a straight line at 700 degrees Celsius in here, the higher surface area will allow you to, this blue line in here will allow you to attain a permeated oxygen rate at 1.5, okay, times 10.3. But what the main thing that you can get in here is that the higher the temperature, the higher the oxygen permeates through your membrane module, through your hollow fiber, meaning that you will get a higher oxygen in the permeate side. Okay, and then the graph in the right hand side in here is basically showing the variations of the oxygen partial pressure at different side. The blue side in here is showing the one on the feed side, the one on the right hand side. So when it reached the point in where basically the oxygen partial pressure meet each other, then we call it an equilibration point. Okay, but that equilibration point may not go into zero. So the most productive conditions you have is when this one goes into the zero. That means you utilize all the oxygen that is available on your shell side. So all of them basically go into the lumen side. So in this case, it's basically capped at 56% maximum. So meaning that this is not really efficient. Okay. So now what we showed in here is if we have a different countercurrent condition. Okay. So this countercurrent condition in essence is basically showing a better performance with respect to the co-current flow. And then it avoids a PO2, positive PO2 on the outlet. As you can see in here, if you go before in here, you see that this one is 0.2. But you go in here, if you make it a countercurrent, then the oxygen partial pressure on the at this particular site will be in particular lower, right? And then if next we go into the effect of the temperature when you put in a vacuum. So in this particular case, you put in the vacuum on this side, so that basically the oxygen in this particular side will go from this side to that particular side. So what you can see in here is that when you apply a vacuum in here, then the oxygen partial pressure is basically determined by the vacuum pressure setting that you put into your hollow fiber module, right? And at the same time, you get a much higher oxygen separation with respect that if you get if you use a sweep gas pressure. Okay, so this one is what we have if we use a counter current with the vacuum. Now, if we apply a vacuum on the other side, for example, then what we get essentially is that the flow of the oxygen will flow to the side, right? It's almost similar performance with the co-current flow performance. Okay, but oxygen permeation diminish when PO2 is slightly added vacuum. So this is a minimal pressure. So I think I will go into the next one again. I think, and then this one is on the effect of the feed air flow rate as when you use sweep gas. So you imagine that you are using a different feed air flow rate. Okay, so this one is what is put in the x-axis. So as you increase the feed air flow rate, there will be a point where the increase no longer contributes much to your permeated oxygen. So this is why this kind of simulation is very important for us to know how high we should increase our feed air flow rate. So for this particular scenario, for example, at 970 degrees Celsius or 700 degrees Celsius, then you will achieve a very low economic point of return if you increase it above, for example, for 500 degrees, 500 mil per minute. Okay, and this again is showing you the partial pressure variations on the feed side on the permeate side, and this also shows the feed air flow rate for the sweep gas when you change it into the counter current configuration, for example. Okay, it's almost the same. For example, so it's if you increase it above 320, then it will no longer give much more economy return. For the vacuum, it's a bit more interesting in here because you can see that if you are applying a vacuum pressure, for example, you can keep on increasing the feed airflow rate up to about 1,500. If you see this this light blue line in here, right? Basically, vacuum is allowing you to attain much more productive. That is, if you can really have a very intact sealing into your membrane, and you can apply a very high feed airflow rate in here. And note, you can see in here that it is much more efficient because you can attain a lower oxygen partial pressure at the end of your hollow fiber membrane in here. And then the insert in here is basically just giving magnifications into this particular area to show the overlapping, to make it more clear. And likewise for the counter current flow, I think this is not much so difference with the previous one. Okay. The next case is when we are talking about the feed air pressure. So how much of the feed air that you need to put in here to change to get a good permeation performance. So for example, this one is, instead of defined in terms of the permeated, in here we are talking about the oxygen yield in here. So the oxygen yield in here is in the big picture, meaning that how much oxygen is available in the feed side that can be recovered in the permeate side. Okay, so in here it's meaning that we, depending on the temperature as well. Okay, so if we are talking about the 1123 Kelvin, for example, then I think we can still get a very high oxygen yield if we increase the feed air pressure up to about 16 kPa in here. Okay, then this is also showing the oxygen partial pressure difference in the feed and the permeate side. And this one is basically the sweep gas as well. Okay, now what is interesting in here is that if you are operating at the highest temperature that we are testing in here, then you don't need to apply as much high as the feed air pressure in here. So for example, you can stop at about 4 point something a bit to get a 100% oxygen yield. And if you do a vacuum, then there will be a little bit of interesting observations in here, because as you can see in here, that this is capped at a value that is less than 100% in here. Okay, so it's near complete, but it's not really complete. Okay, and that depends again on your vacuum pressure. So basically, in the real conditions, then it depends on how good is your how good you can achieve your vacuum pressure. Likewise in here as well, as you can see, it's almost the same. It achieved a near complete, but it's not really complete. Okay, and this one is basically showing the effect of the sweep gas flow rate. So if you are dealing with the sweep gas flow rate, like how fast you need to pass your sweep gas flow rate on the lumen side in here. Okay, as you can see in here that for example, above 300 in here, it's not very more economic for you to increase the sweep gas flow rate anymore. Okay, and it's kept to 90% at the maximum. In here, you can attain the highest oxygen yield by capping your sweep gas flow rate at about 500 for this 1123.15 K, for example. As you can see in here, the separation of the oxygen has been complete. So above this particular point, then there will be no more transport of the oxygen beyond this point, beyond this 17.5 points in here, for example. Okay. And this one is the effect of the vacuum pressure. For example, if you change the vacuum pressure, for example, you want to start from the right-hand side, but ideally when we are talking about the plotting, then people want to see low going into high. So that's why we are plotting it not 0.1 in here to 0.001, but instead the other way around. Okay, so
Excuse me, Dr. Jaka.
yes.
The needs again. Thank you.
Okay, thank you. So what you can see in here is that as you decrease the vacuum pressure, you don't need to really go into below 0.01 vacuum pressures in here for this particular case. Okay, you just want to get into a point where the change is quite reasonable, because if you keep on lowering it beyond this point, then it will have no use as well, for example. And we know in here that the separation has been quite complete up to here. Okay, and this is the same one as well. It's just you see that there is a little bit of a weird trend here that you see, because we are putting a vacuum on this particular side in here. Okay, so the pressure should go down from this particular point to this particular point if we are following the model correctly and applying the boundary conditions correctly. So in conclusions, we have shown you the simulation studies. It's not as only simulation studies. Actually, we have given you a picture of how the simulation studies, the experimental and simulation studies of the MIC hollow fibers has been done using the Tanley model. And sweep gas mode is basically allowed to achieve the complete auto separation in counter current flow configurations. However, it requires a sufficient driving force for better efficiency. For vacuum mode, the performance is practically similar at different flow configurations. So no matter you do a co-current or you do a counter current configuration, it will not have a much differences. And it's able to operate under large feed airflow rate efficiently. Okay, so that will be the conclusions for the today's sessions. So I would like to thank all the co-authors and then also who are involved in this research project, because this project has been very time consuming. It involves not only the experimental project from the different institutions, but also a very careful MATLAB coding, and then designing, and then developing and troubleshooting as well. Okay, and then this has been made available. This work has been enabled by the funding support from the various agencies, from my collaborators, of course. And then I would like to thank again organizing committee and the top management from the Universitas Diponegoro to invite me to come over to this for sharing for this conference. And I would welcome everybody that are interested to contact me regarding this work or any opportunity to work with us in this area or in the particular area that I showed before. Okay, thank you so much.
Yeah, thank you, Dr. Jaka, for the visionary presentation. Now, we have our discussion here. So maybe for the participants, is there any question? You can use the raise hand menu for asking question. Okay, while with some questioner, Dr. Jaka, I would like to ask a question.
Yep. Yes.
So, yeah, maybe I underline that the conventional cryogenic separation produce more than 99.5%, although it have high capital cost. The pressure swing adsorption provides lower capital cost. However, the purity less than 50%. Therefore, this study discusses about the employment of mixed ionic electronic conducting membrane for oxygen separation. Here, we show before that many simulation mode already applied, which some of them can provide up to 100 oxygen separation. And my question is, how about the capital cost in regards to the operational cost, since some material using rare earth metal element of La? So would you like to explain about this,
Yep.
Dr. Jaka? Thank
you for the questions. It's actually this technology is still on the development scale. So if for example, if we are talking about this, the techno-economic analysis at the moment is not very clear, but in terms of the carbon capture and storage, if we do apply this MIC technology into the combustion, into the clean coal combustion, in particular the oxy-fuel combustion, for example, then people have shown that there will be about 30% of the reductions in terms of the operating cost that is possible from this technology. Okay. And that, but at the moment, I think because this technology is still under development, so we don't really have a clear picture yet as to how the operating cost will be reduced in real conditions. Okay, but in essence, in here, instead of wasting too much energy on basically going down to very low temperature, we have a process that are hot already. So we just integrate the energy. And that will be working well, assuming that the sealing and all the other aspects of the technology is already matured, basically. Okay, so for those questions that are related with the development, the maturity, and the techno-economic analysis, I would suggest to refer into this advanced functional materials roadmap that our group has recently published with the other professors in German, and that will give much more insights into this, because the hollow fiber membrane that I presented in here is not the only geometry that is available. And for example, people in German, they make it in the planar geometry. So they make it in terms of the membrane sheet. Okay. And then they make it into probably like 100 or 300 of those stacked together. So they can achieve about similar performance. But I think that those German people are very practical people, so they may have a reason as well that is different with us in using the hollow fiber membrane. I hope that answers your questions.
Okay, thank you for your answer, Dr. Jaka. Here we have Mrs. Sri Utami, which already raised her hand. Okay, for Mrs. Sri Utami, you can ask directly to Dr. Jaka, please.
Okay, thank you very much, Dr. Jaka. My question is almost the same with Mrs. Vita about the cost. As you mentioned earlier, in the separation of O2, there are a large driving force required.
Yes.
Then in the application, how is the ratio between the cost required for driving force and fuel efficiency? Okay, thank you very much.
Okay, in terms of the fuel efficiency, the one that I know from the lab scale is that everything is still in the lab scale. So meaning that we normally use those furnace that we are using. Okay, but the driving force that we create in here is normally we compress it from the gas. But in the real situations, I think if we use a compressor, then that will be, I think, the major cost of where the pressure is. But even if you are using a compressor, I think if you can produce a very high purity of the oxygen, I think then that will create the economy gain for this technology. I think look, for this particular technology, the one that I'm talking about is in real application. Actually, they have a two segment. The first segment is you just want it to get a very high purity of the oxygen. Okay, so that means you don't really have to deal with the material stability, because there are established material like BSCF that you can use for long operation time, where you can just apply a vacuum site on the premise site. But of course, the main cost will be on the material and on the energy side. But that will be interesting as an alternative to the cryogenic separation. But the other market segment that I mentioned to you, the oxy-fuel combustion, that one will be a very large scale. At the moment, the bottleneck is the membrane stability, because the established membrane that have a very high oxygen flux, okay, if they are exposed to the CO2, to the carbon dioxide, then they will react. So if we operate for the oxygen permeation in such conditions where the CO2 is present in a high concentration, then the membrane will be degrading very, very quickly. So at the moment, the research progress is going into inventing the new material that can be operated stably in that particular environment with reasonably high flux, because there is a trade-off in this particular area, meaning that the membrane that have a very high oxygen permeability is generally not very stable over the long term. So that's why I would say that the 30% of the reductions for that oxyfuel combustion, if we apply this technology, is really a rough picture of the techno-economic analysis that we have at this stage. So the detail at this moment, I don't really have in my mind.
Okay, thank you very much.
Okay, thank you, Dr. Jaka, for the interesting discussion. I have one question again, Dr. Jaka, since we still have time also. Since we applied gas here at the high temperature also, is there any specific maintenance during while we were using this membrane? Okay, thank you, Dr. Jaka.
Ideally, if we are talking about the industrial scale, then those industry people are very practical. They would not want something that will create them trouble when they shut down. So the bottleneck of this technology is the temperature, because when you want to start up this technology, you have to increase the temperature. The temperature have to be increased from 0 up to about 900 degrees Celsius. So that 900 degrees Celsius is a very high temperature, right? It's when you increase the temperature, when you heat up, then there will be a problem in terms of the material expansion and the sealing expansion. So that's why the bottleneck of this technology will be, instead of in the gas or in the other thing, the maintenance will be on the sealing and on the thermomechanical side of that thing. So it's very important that we have a very good system that can afford for that expansion, such that when you start up and shut down and operate, as you cycle the temperature and you put in the gas and I think pressurize it and then apply a different pressure on the different side, that can sustain over, let's say, continuously for without non-stop probably for at least like 2 weeks or more, I think, while you have another unit that get prepared ready on that one. So again, as what I said previously, I think it's still on the pilot plant scale, but it's not really a full-on industry scale yet at the moment. So still much thing to be done on this respect.
Okay, thank you, Dr. Jaka. Here we come to the conclusion, and I'm going to emphasize that the vacuum mode exhibits similar oxygen separation performance by applying both co-current and counter-current flow configuration, and becomes more desirable as the sweep gas mode loses its oxygen separation efficiency. I really appreciate to Dr. Jaka for giving us the advanced information about membrane technology. Hopefully this keynote speaker session today will award benefit to all participants. And before the closing session, the organizer would like to deliver a certificate as a keynote speaker by displaying it online. Okay. Yes, this is the certificate of appreciation to the Dr. Jaka, Associate Professor Jaka Sunarso. Thank you very much for your coming in our IKEAS 2021.
Thank you so much, everybody.
And we will have a session break and transition time in around 5 minutes, and we will come back to the sharing session. Thank you for your Thank you for all your active participation in this keynote speaker session today. Thank you very much.
Thank you so much for the moderator and keynote speakers. Now let's move to sharing session. Sharing speakers are Dr. Atika Kadri from Teknologi Mara University, Malaysia, and Dr. Novi Heriono from PPSDM Megas Cepu, Indonesia. In this session, we'll be leading by Mrs. Sri Utami Handayani. Please extend a warm welcome to the moderator, but let me read the curriculum vitae first. Mrs. Sri Utami Handayani, University, and her main research is about drying area. To Mrs. Sri Utami Handayani, from whom the time has been allowed.
Okay, thank you very much. Good morning, ladies and gentlemen. Assalamualaikum warahmatullahi wabarakatuh. Honorable Professor Dr. Insinyur Budiono, Professor Hidepumi Yosi, Associate Professor Jaka Sunarso, and all the Dean and Lecturer from Partner University. Honorable Mrs. Atikah Kadri, PhD from University of Technology Mara, and Mr. Novi Heriono from Pusdiklat Migas Cepu as our invited speaker, and honorable distinguished guest, conference delegate participant of International Conference on Chemical Engineering and Applied Science 2021. It is my honor to be the moderator of this sharing session. And it is my honor also to have Mr. Atikah Kadri, PhD, and Mr. Novi Heriono here this morning. Mrs. Atikah Kadri will deliver the speech with the title of Green Hydronic Pathway, Potential of Non-Gaseous Hydrogen Storage Medium. And Mr. Novi Heriono will deliver the speech entitled of Employability Skills of the Winner in Oil and Gas Industry. Before we begin this sharing session, may I briefly introduce our invited speaker. Mrs. Atikah Kadri, PhD, finished her bachelor from Chemical Engineering with Fuel Technology from the University of Sheffield, United Kingdom. And then Master of Science from University Malaya, Malaysia, and PhD in Advanced Material, University of Queensland, Australia. Her research interest is about hydrogen storage, catalyst, microwave extraction, solid waste management, and engineering education. And now Mrs. Atikah Kadri work as senior lecturer in Fakulti Kejuruteraan Kimia, University Teknologi Mara. And then Mr. Novi Heriono is a trainer and assessor in oil and gas production and education management. He finished a bachelor from Diponegoro University, and then Master of Engineering from Institut Teknologi Bandung, and PhD from Universitas Negeri Semarang. He has a lot of license and teaching experience about oil production and education management. For this sharing session, Ms. Atikah Kadri and Mr. Novi Heriono will each deliver their presentation for about 30 minutes, and then followed by question and answer session. For all the participants, while the invited speaker give their presentation, maybe you can write the question on the chat room, or maybe after the presentation, you can also ask your question directly. All right, Mrs. Atikah Kadri, now the time is yours.
Thank you so much. Assalamualaikum warahmatullahi wabarakatuh. Before I proceed, I just need to check whether the audio is received clearly at everyone's end.
Yes, clear.
Thank you. So let me just share my material. So is the slide visible?
Yes,
All right. All right, thank you so much for the introduction. Once again, I'd like to I really appreciate this invitation, and I believe that everyone here are very eager to learn new things, and I myself here are so fascinated with the last two presenters with so in-depth discussion. So I hope that my sharing session today able to spark some interest or perhaps create some collaboration opportunities later. Okay, Rabbi shrah li sadri wa yassir li amri wahlul 'uqdatam min lisani yafqahu qawli. I bid thank you to the chair lady with the kind introduction. And today I'm planning to share with you a topic which I think very much relevant to what is happening right now, is an option of hydrogen, an option of energy substitute, and particularly looking into green hydrogen pathway and looking at a storage medium which is in non-gaseous form. So I'm Atika, and I'm actually coming from this very lovely university. It's actually a largest university in Malaysia, and we have campuses throughout the states. And we open for academic mobility for both students and staff. So we really invite to everyone to join us. And we also welcome international students as to join our postgraduate courses. Right, so this is actually the engineering complex where it's stationed all these bright minds and enthusiast researchers doing their lab work and activity and teaching and learning activity. Okay, so let me just give a brief walkthrough of what to be expected in this probably 20 minutes presentation. I'll be talking about the research background and motivations, and I'll be elaborating a little bit on the material preparation that the research work is devoted to. And I also going to elaborate on the findings, which includes the morphology, the performance, as well as concluding into the possible mechanism involved when you have non-gaseous hydrogen storage system. And finally, I'll conclude this presentation and share some way forward in terms of the research work itself. So I believe everyone are aware that at this point of time, the COP26 is actually taking place in Glasgow, and they are actually talking about how we can actually make sure that the carbon or the source of carbon are put into minimal. And in terms of one of the agenda is to make sure that the cars or the transportation are being switched to electric sources, as well as investment in terms of renewable activities. So of course, this is an alarming condition where we know that the sources of this climate changes are due to the release of carbon dioxide, and obviously industries as well as the users like myself owning a car would also have the responsibility of thinking of an option to reduce this carbon or to achieve net zero carbon in 2050. So by looking into that perspective, an option of having a hydrogen cell fuel car or electrical car it's a good option. And what I'm planning to address today is something to do to couple hydrogen fuel cell, whereby it requires to use hydrogen. And if we were to look at the larger economic point of view of hydrogen economy, we have actually seen that a lot of systems or a lot of application are at the end where they are ready to receive a hydrogen fuel cell, hydrogen fuel. So we have, for instance, in Japan, they already use hydrogen to heat their spaces as well as to power their systems. And in terms of chemical industrial processes, well, hydrogen is really part of the resources that have been required in metal production, for example. And in terms of energy usage, it is well accepted, and most of the giant industry are thinking of switching from using fossil fuel to this very friendly and very environmental friendly hydrogen material. And if we were to zoom down to the hydrogen, green hydrogen, I would like to look at electrolyzers, one of the source of green hydrogen production. And the amount of hydrogen produced by the electrolyzer able to power ships or even cars, or it can also be complementary to gas power plant, for example, for electricity grid. And all these facilities, all these areas requires storage. So we can't just have an electrolyzer individual to run the car, or we can't have this electrolyzer just to heat up your house at this point of time. So there will be an issue on how we be able to cap this hydrogen and distribute this hydrogen to the users. And when we talk about users, we have massive users. For example, like gas power plant, it requires a huge amount of gases flow rate. So indeed, storage hydrogen is something to look into, and we need to dwell at what are the challenges involved when we have hydrogen. Now, these are some of the common hydrogen storage options that are available right now. And I think the most common one is the pressurized tank. And well, this is not something new. We know that when we have gases, most of the time we will keep these gases in pressurized cylinders. In terms of the volumetric density, it is not that attractive as compared if you keep hydrogen in cryogenic tank. However, having a cryogenic tank requires extra energy because it requires a very low temperature, and that probably put off the interest of looking at cryogenic tank as an option available for public. As for pressurized cylinder, you obviously know that it requires very high pressure, and it could reach to 800 bar. And then it requires a very strong and light vessels, enabling to make sure that safety are being well kept. In terms of physics option, it is something people have been investigating, using carbon nanotube, using very porous media to keep the hydrogen. However, in terms of its quality of volumetric density, it is rather low as compared to the rest of the options of hydrogen storage. Even though the pressure is quite reasonable, but the mass weight percent as well as volumetric density, it is something need to be looked into if we were to have this available. Now, that brings me to another option of hydrogen storage, which is by using metal hydrides. Now, interesting about metal hydride is you're able to work at a relatively low pressure, which is about 20 bar, and it is very high in terms of volumetric density, which translate us to a smaller size to keep similar amount of mass of hydrogen. So it is very attractive when we talk about size, especially when you like to have this available on a light vehicle, for example. Like Toyota Mirai, it's actually using a compressed gas tank where it runs at 700 bar. And with a mass weight percent about 5.7 weight percent. So if we were to look at the volumetric density, it is very it's not that attractive because it requires space, and who would want to have a huge car just to keep a hydrogen tank instead of having the luggage or having the passengers in the car. So that really makes me think that we need to think of something which is compact and at the same time having sufficient amount of hydrogen to run a car, for example, for a good 600 or 700 kilometer ride. So we end up on investigating hydrogen storage material where it actually applying a hydride forms, and we need to look at a good example or a good sample to able to keep hydrogen reasonable for example, in order to apply for transportation purposes. So we end up with going to magnesium material. Okay, so why we choose magnesium? This is purely because the magnesium is reversible in terms of the reaction with hydrogen, because what we want is we would like to have the hydrogen to be absorbed and at the same time allowing that hydrogen to be released to be used for the application. So if we were to look at on that note, magnesium hydride indeed is a good candidate for this storage, non-gaseous material storage. And apart from magnesium are being so abundantly available, so it is actually one of the elements that is abundantly and nobody cares about magnesium. So I think it is good option to go for magnesium as one of the storage material medium. Besides that, magnesium is relatively light. So when you plan to have that for mobile application, for transportation, it is a good candidate because that would not put extra luggage to the transportation unit. And the fact that it is having sufficient amount of weight of hydrogen in a system and able to work at a relatively low pressure. However, even though magnesium does not promise sunshine and also doesn't promise rainbows, there are challenges that need to be considered, especially when we talk about the reaction or the reaction between hydrogen and magnesium. It is actually an ionic bond. So having this would actually have a cost in terms of requiring high operating temperature, and this obviously will hinder the kinetic, or it will slow down the kinetic, and this probably not going to be one of what we like to have when you charge your car. So what is the objective of this work that I'd like to present to you today is we'd like to improve this absorption and desorption kinetics, and we'd like to alter the thermodynamic barriers so that we can have a relatively high kinetic for charging and discharging, as well as able to work at relatively low temperature. So let's move on to how we end up making one. So this process of producing magnesium hydride storage material is a rather simple process in which it involves a dry milling condition, and we employ high energy ball milling machine. And in this system, we only need a steel ball Okay, so this steel ball must have a ratio with the powder that we put in with a ratio of 40:1. Okay, and the magnesium that we use are in powder form to improve the kinetics as well as to alter the thermodynamics. We actually make use a few additives, and some of them are for example, complex catalysts or metal organic framework as a catalyst, and we couple them with a carbon nanotube. So the process itself is very simple. What you just need to do is you just need to load 5 weight % of these additives into the system and allow milling process to take place, ranges from 4 to 5 hours. So at the end of the milling process, you should be able to get a composites that are very, very sensitive to moisture and air, because we're dealing with magnesium. Magnesium is easily being oxidized. So we need to work, arrange this unloading and loading inside a glove box. So once we got this, the product, or once we synthesize this hydrogen storage material, we send them to to analyze them. And first stop is we're going to look at the morphology of the product. This I have here is the TEM image of the magnesium hydride, which is being coupled with metal organic framework and carbon nanotube. And we conduct an EDX element analysis just to check whether or not the additives are properly being distributed or dispersed in the main magnesium hydride material. And we got that with this spot analysis, we found that the additives are well dispersed. And from the TEM image itself, we able to see that the product out of this high energy ball milling are actually in a very small sizes, which is easily less than 10 nanometers. Right, so in terms of the absorption and desorption performance, we have tried, a list of additives starting from the carbon nanotube, a combination of complex catalyst with carbon nanotube, a combination of metal organic with carbon nanotube, and in fact, we have actually moved to having a bimetallic metal organic framework as a catalyst. So along the way, we found that having a carbon nanotube would actually accelerate the absorption, and it is clearly shown there by the absorption weight %. If we were to add carbon nanotube, we could reach easily 6.5 weight % in 1 minute, and this absorption temperature is at 200 degrees C. And same goes with vanadium complex catalyst. It reaches about 6.6 weight %. And our venture into bimetallic metal organic framework also give similar about 6.5 weight %. So that makes us think that why having CNT and metal organic framework will assist this absorption or increase the kinetic. We noticed that the CNT and MOF have a common characteristic. Both are porous material. So indeed, this porous passage or pathway is actually allowing hydrogen to be able to reach to the surface of magnesium, so that this surface of magnesium can react with hydrogen to produce magnesium hydride. The challenge about creating magnesium hydride is these new free surfaces would be hindered if you have a layer of magnesium hydride on top of it. So the idea of having CNT and metal organic framework is to allow access of hydrogen to the fresh magnesium surfaces. So if it can penetrates between this magnesium hydride surfaces, we could get more hydrogen being reacted with the magnesium metrics. But most importantly, I'd like to highlight that by reducing the bimetallic metal organic framework, so the one that we try by using bimetallic metal organic framework is without reduction. So we have 6.58%. However, if we reduce the bimetallic metal organic framework, we notice that the absorption capacity increases to 78%. So I'll be showing to you why this happened in a moment, but what I'd like to highlight again on this table is the performance in terms of desorption. So we have quite, we are actually moving we show some improvement in terms of desorption. However, if we compare with the magnesium hydride capacity, we should reach to 7.68%. Unfortunately, we still unable to reach to that par. So we were thinking about how that we can actually improve the desorption kinetics, and furthermore to reduce the temperature from 280 degrees C to lower, so that it able to apply for more application. Right, so let's talk about why carbon nanotube able to improve further hydrogen storage kinetics. Okay, so on this chart, I have here the Raman spectra of the sample medium or the magnesium storage composites. So at the top, we have the magnesium hydride, which is just being mixed with CNT using mortar and pestle. So it's not by using high energy ball milling machine. So same goes with the one the below CNT, where we have MV CNT mix. So this is where you have the complex vanadium catalyst, which is mixed by mortar and pestle together with carbon nanotube. And if we look at the G band, it is very sharp, okay? And there is not so much of D bands available for those two samples. So from this observation, we realized that if we have high energy ball milling, that would actually impact the G and D band of the samples. Now, why it's so important for us to know the G and D band of Raman spectra? Because the ratio of the intensity of D bands against G bands will tell us how much the sample, or how much is the carbon nanotube being destroyed or having a defect. So theoretically, the more the defect, the carbon nanotube, there will be more functional group that is attached, and that will be able to assist attraction of hydrogen through that carbon nanotube. So we investigated further, where we use different milling time with the carbon nanotube, and by reducing the milling time as compared to those at maximum milling time of 5 hours, we reduce the milling time to 4.5 hours, as shown as the third Raman spectra. So at the third Raman spectra, we actually can observe that the G band and D band are present. So that is telling us that there is a defect. So carbon nanotubes are being defected due to high energy ball milling processes. And not just that, we be able to see the ratio of the intensity of the D band and G band. We got to see that the magnesium samples that is being milled in a shorter period time as compared to 5 hours, able to give relatively high absorption kinetics. So if you look at the absorption curve at 200 here, so we able to show that the curve noted by the green symbols is referring to the one that have a optimum milling time. So if you go beyond than 4.5 hours of milling with the CNT, you'll be able to see that there is a drop in terms of its performance. So it requires probably nearly about 6 minutes to actually achieve to a capacity of a shorter milling time. So from these findings, we can conclude that yes, milling CNT is good because we create defects and that will promote hydrogen to pass through the carbon nanotube. However, if we overdoing it, we are losing the function of the to attract hydrogen to pass through the carbon nanotube to reach to the clean magnesium surfaces. Okay. Right, so moving on. So this is a result that we got from the absorption performance test on a metal organic framework. What I'd like to highlight here is the magnesium hydride coupled with metal organic framework enable us to have as low as 100 degrees C absorption. So in this case, we can see that you could have on the left chart on the left, we can actually have hydrogen being absorbed at 100 degrees C. And it takes about probably in 10 minutes to actually achieve to more than 3.58%. So this indeed an exciting findings because we know that by strategizing to have metal organic framework and carbon nanotube allows us to have a lower temperature for absorption and to magnifying what exactly happened. On the right hand side here, we have the comparison between all the samples. Obviously, M4 is referring to the magnesium, pristine magnesium, so it will take probably ages to absorb hydrogen. However, having some additives, for example, having carbon nanotube, having the vanadium morph, as well as having combination carbon nanotube and vanadium morph is able to enhance the hydrogen absorption performance on the material. So this is interesting because we are still struggling to find ways of reducing the temperature lower than 100 degrees C. So we expect to have more breakthrough in terms of formulation, which able us to go beyond lower than 100 degrees C. Now, I've mentioned to you about what does MORPH do? What does metal organic framework do in terms of the performance? And over here, I have the XPS data that we have a narrow scans and on the left side is the catalyst XPS data, where we have over at in figure A and B, we realized that the metal organic framework, fresh metal organic framework that we synthesize, when we run the XPS, we are unable to see any zero valence of the additives, in this case, nickel and cobalt, right? But when we reduce it, and we notice that there is a zero balance cobalt and nickel. And then we use this reduced nickel morph, and we add to the system to produce the magnesium storage composite. And from that reduced nickel morph, we actually able to see, so on the left-hand side, the four chart on the left-hand side, A, B, C, D here. So we can actually see that the zero balance of nickel and cobalt is more apparent when we work with the reduced nickel morph instead of using fresh nickel morph after right after the synthesis. Now, if we compare with the hydrogen absorption, okay, so this is not desorption, it's hydrogen absorption. And we notice that if we were to use the reduced nickel morph, we able to see that the performance is much better, okay, as compared to the fresh nickel morph right after the synthesis. So the blue and the red curve represent those which has been reduced. One is reduced for 5 hours, another one is reduced for half an hour. So from this XPS result, we can conclude that the active sites are actually coming from the zero balance of the nickel and cobalt. As for the desorption, we have tried looking into the TPD, temperature pressure desorption investigation, and we look at where is the peak where hydrogen is being released. So the first two on the left is by using complex catalyst, and the next two on the right is by using metal organic framework. So if we compare between the complex catalyst, we realize that combination with carbon nanotube able to reduce the onset temperature. So if you compare from its pristine magnesium onset, is about 320 degrees C. So if we add complex catalyst and carbon nanotube, we're able to reduce the onset temperature to as low as 173 degrees C. As for the metal organic framework, we also able to reduce the onset temperature to as low as 166 degrees C. So, well, onset is where hydrogen starts to release. So then it's a good sign that the activity of the releasing of hydrogen can take place as low as this temperature. So this could be our target temperature, as low as 166 degrees C. For desorption performance, over here on the left side, we can see that having a combination of carbon nanotube as compared to those without having carbon nanotube would have a difference in terms of the kinetics, right? And in terms of the temperature reduction, we'll be able to reduce as low as 260 degrees C. Again, the kinetics is rather sluggish. So we need to think about what to be, how do we alter the thermodynamics property so that we can actually reduce the temperature lower than 260 degrees C. So in short, having at 300 degrees C, it takes about 10 minutes to actually release the hydrogen at the rate of 6-8%.
I'm sorry, Mrs. Atika.
Yes.
Your time is left 6 minutes.
Okay, thank you. Right, so I'm approaching towards the end. So this is just a little bit of the thermodynamics bit. We have actually looked into samples that runs with MOF and carbon nanotube, and we found out that the desorption enthalpy and desorption entropy are slightly lower than the pristine magnesium. In fact, by having the additive like carbon nanotube, the metal organic framework, as well as the combination of both, able to reduce further, okay, able to reduce the desorption enthalpy to as low as 71.3 and the entropy to as low as 126.4. So indeed, this is something that obviously telling us why does hydrogen can be released at such lower temperature, relative lower temperature, because the fact that we had actually altered the thermodynamic desorption properties. As for stability, we also run an experiment to check whether or not does hydrogenation, dehydrogenation, or absorption, desorption would actually alter the performance or the capacity of the magnesium hydride sample. So we did that for at least 6 cycles, and we got to find that the stability is rather intact. We'll be able to have the same performance for absorption at 200 and desorption at 300. And in fact, if we look at the XPS data, narrow scan, we also find out that the valence of vanadium, in this case sample is used vanadium, the valence, zero valence vanadium are present throughout all the samples. So that is a good sign, showing that stability of this storage material. Now, moving on, I guess this is the final bit, is about the mechanism. What we have actually worked on is we add additives in the magnesium matrices, and we distribute this catalyst and also carbon nanotube, or in the case of metal organic framework, are all being distributed well in the hydrogen matrices. So what we are proposing is the hydrogen gas will dissociate it as it reaches to the surface of the catalyst, and that would actually dissociate the hydrogen gas to its atoms, and these atoms are being attracted by the carbon nanotube due to the defects of the carbon nanotube, which channeling this hydrogen to the free surface or fresh surface of magnesium. So the opposite, or the desorption mechanism, on the other hand, would be on the opposite direction, where all this when the hydrogen is exposed to a vacuum condition, so this hydrogen will then make way through this CNT and eventually leave the CNT and combine itself to produce the hydrogen gas. So this is what we proposed, where carbon nanotube provides the channeling, diffusion channeling, and the catalyst or the additives work as the active nucleosides. So conclusion and way forward. What we can actually conclude out of this work is metal organic framework is highly thermostable material that able to have maintain its property in the hydrogen, in the magnesium matrices, and it can withstand cyclic stability, and at the same time with the very large surface of metal organic framework or carbon nanotube allows more intimate contact between the hydrogen as well as with the surface of magnesium, and this will obviously catalyze the reaction between magnesium and hydrogen. And on top of that, having a micropore structure like a metal organic framework, carbon nanotube works as diffusion channel, which enhance the storage properties. So in the end, what we actually achieve is basically we have a compact hydrogen storage material, which is storing hydrogen in non-gaseous phase, and it has an excellent reversibility as well as have an ultra-fast charging, which is less than 1 minute. And the way forward, we look into the possibility of using this material for bulk hydrogen transfer to be used for exporting hydrogen or transporting hydrogen from one point to another. So we're probably not going to be using any pressurized vessel to deliver your hydrogen. And at the same time, in terms of the material development, we should be looking into the desorption performance, particularly at nanostructuring strategy, where we could create more direct contact with the catalyst on the surface of the magnesium for storage purposes. So with that, thank you so much for your attention. I'd like to acknowledge University Technology Muara for sponsoring and also for supports, and the University of Queensland, Australia, for making this work possible, as well as Australian government, Australian Research Council, as part of the given the grant. And I also would like to call upon any collaborators who felt that having the same interest or probably can venture or expand the work. I would call everyone who would like to collaborate, and perhaps we could actually discuss this further. Feel free to email me at atikakadri@uitm.edu.my. Thank you so much for your attention. Assalamualaikum.
Waalaikumsalam warahmatullahi wabarakatuh. Thank you, Mrs. Atika, for your interesting presentation. And now, for the second invited speaker, Mr. Novi Heriono, the time is yours.
Okay. Good afternoon, Mr. Tami and all participants.
Good afternoon, Mr. Heriono. Novi.
Audio is see clearly?
Yes.
Yes,
The
okay,
voice
thank
is
you.
clear and the slide also shown.
Okay, thank you very much. Okay, thank you for opportunity so that I can share the experience about what skills are needed in oil and gas industry. The topic is related to future challenge of a career in oil and gas industry. What is needed, what is expected, what should be prepared, and especially for graduates. So before getting topic, let me introduce myself. My name is Novi Heriono, but call me Novi. Yes. A little feminine, but okay, yes. This dissertation topic, praktek kerja industri manajemen model in of vocational high school student based on project based learning, and now relate to magang Merdeka Belajar in Indonesia. Yes. Okay, today's condition oil and gas industry in Indonesia, we can see main upstream oil and gas project. Yes, there is still many potential source of oil and gas industry in Indonesia, spread all over in Indonesia. In addition, there are refinery project and refinery development to meet domestic energy needs. And new project, we can see Buntang Refinery in Buntang, and we can operation in 2025, 300 MBCD, and Tuban Refinery, Pertamina and Rosneft project operation in 2024, and the development project, we can see Cilacap Refinery, Balikpapan Refinery, Balongan Refinery. And now we choosing three characters of energy industry. One, high technology, high cost, and high rise. The challenges: globalization, industry 4.0, 21st century skill, and the pandemic. We expectation maybe working at national company, multinational, international industry, or being entrepreneur. But we look existing condition. Yes. For graduated self-understanding to reflect the expectation and the challenge. Look at challenge. Industry 4.0, three main characteristics: innovation, automation, information transformation. And now 21st century skill must be digital age literacy, inventive thinking, effective communication, and high productivity. In global pandemic, Look at low processing power, new normal, adaptive, global dismissal, and higher competitiveness. In the globalization, yes. Human resource ready to work in priority or free labor between countries. No. We can choose, yeah. This expectation, working at energy industry or being an entrepreneur in energy sector. Look at job vacancy in Bahasa, yes. Or in English, we can look the skill in red. You can say hard skill. In blue, we can say soft skill, and yellow, teamwork and personal skill. So we must self-reflection. Okay. Employee skill is skill required to join energy industry and to have successful career. Yes. And now for aspect skill, hard skill, soft skill, personal management, or teamwork. Yes, teamwork. If you want to divide into hard skill and soft skill, look, my research in 2020, we research employee perception on vocational high school graduates, employability skill needed in today's oil and gas industry. Yes. The sample, there are 164 operator or technician in oil and gas industry or division, and 26 supervisor. The questionnaire adapted from survey of the employee skill need in workforce designed by Jason Robinson. And the study aim to determine the industry competence that are most needed in oil and gas industry, according to perception of the employees. And we can look the result of the study in the 7 skill needed into the oil and gas sector. And 1, the skill to prioritize occupational safety, the skill to work together in team, the skill to apply theory into practice, the high learning motivation skill, the problem analysis skill, the skill to be adaptive to change and dare to make quick decisions. The result, the employee skill learning can be implemented in the university or school or the workplace through in the internship program. Hard skill can be learned, evaluated, and measured. How to apply in industry? Pay attention for aspect. 1, in university. In university, from the philosophy of basic science to organization concept, we can learn. And 2, training. Training, sharpening skill of process and equipment. Has a occupational risk assessment, basic technical knowledge oil and gas, regulation of oil and gas, PNID, control and logic system, computer engineering software skill, and equipment simulator. This is hard skill for the training. 3, for internship, learning in industry based on industrial working culture. and now in program Magang Merdeka Belajar and 6 months between university and industry. And the last, graduates can be certification, proving skill by competency assessment. The first aspect to be considered and proven by competency certificate. How to soft skill? Soft skill in oil and gas industry can be related to 3 soft skill in fundamental, communication or language, presentation and report, HSE culture, health, safety and environment culture, ethic, industry ethic, problem thinking and solving, analytical, and decision making. In the personal management, or acting in industry, you can develop positive attitude and behavior. Be responsible, be adaptable for change, continuous learning, safe working, fast response to college and superior, and resourceful. The last team working skill, working the other, proactive, helpful, participating in project and tasks. They are soft skill related to 21st skill in industry now. How to heading to improve the skill? We can start vocational university graduates, high GPA, punctual, and we can develop employable skill, hard skill certified, soft skill certified, personal management, team working, and reflection and continuous improvement. So we can do winner employees in oil and gas industry. To provide soft skill, their CV development skill must be attractive. CV development skill must be attractive, focus, and complete with required certificate. So we have learning in training or competency certificate, psychological test, practice, rehearse by using various test model, and learn interview skill, intensive practice, rehearsal based on job or position type. The skill can be learned from the university. So we can discuss basic communication and language skill, presentation and reporting skill, analytical skill, and decision making skill. And advanced supervisory skill, leadership skill, coach for performance and negotiation skill. And the last, embodied skill, surveillance check. If you fresh graduate and now are you still employed, how many job applications have you sent? How many times have you received job test calls? How many times have you received interview call? How many times have you passed the interview? How many times have you got offering letter? And if you experience, how long have you been working? When was the last promoting you got? When was the last time you got a rise? If there is 40% layoff, are you working, keeping, and why? Thank you. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh. Thank you very much, Mr. Novi Heriono, for your presentation. And it is very useful for us as a lecturer in the university and vocational school. All right, now is a question and answer session for all the participants. You can ask directly to the presenter, or you can write your question in a chat room. Okay, while we wait for the question, maybe I will discuss something with Dr. Novi because we have a quite same area. All right, Dr. Novi, I want to ask your opinion regarding this pandemic. What do you think about online practice and then online training or even online internship? How to ensure that students can competence in their subject, or maybe how to ensure how student competence can be achieved? Thank you.
Is guidance and standard.
The important is guidance standard. We can give this standard for the online training or online learning, and we must be enter the offline for the fully learn. So in oil and gas industry must be practice. In online learning is very online learning is in the standard and guidance are confirmed initially. The implementation can be smoothly. In oil and gas industry or in PPSD Migas, we can online certification and online learning, but participant must be in industry. They are so the completely work. If the learning in university maybe must be offline.
Okay.
Very empty learning. It must be offline. Yes.
Yes, correct. Because we are in the university, sometimes also headache facing the situation because some subject we need to practice, all right. Yes. But then we only can do the teaching by online, so sometimes it's quite difficult.
Yes.
Okay, and then maybe all right. This is a question for Mrs. Atika. Maybe we turn the question to Mrs. Atika first. Hello, Dr. Atika. First of all, let me introduce myself. My name is Fitria Arifina. I'm student college from Vocational School Diponegoro University. I want to ask about what is the parameter used to develop nanostructure hydrogen storage material. Maybe that is a question for me. Thank you so much, Dr. Atika. Okay, please answer.
All right, thank you so much, Fitria, for your interest. When you talk about parameters for particularly meant for nanostructured hydrogen storage material, one of things that you need to make sure that the material, what kind of mode of storage that you intended. Are you intended for interstitial reaction, or are you intended for physisorption? So if you're interested to look into physisorption, you must make sure that the material that you develop must contain porous media, porous structure, and that porous structure is in nano size. So that is one way if you were to look at for a physisorption. But if you're planning to look at hydrides or interstitial condition, you need to make sure that the material that you produce reaches to that size, and that involves in reducing the particle size to nano sizes, whereby you could have that in using ball milling machine or using infiltration. So you could use infiltration by using a nano-structured porous material, where you infiltrate your material into this porous medium. So you also can have interstitial interstitial hydrogen reacted to the medium. So what I can, in short, what you need is to make sure that your system able to reach to that nano sizes. So that's my response.
Okay, thank you very much. Okay, well, while waiting for the question, maybe I want to ask Dr. Atika about your research. And regarding development of nanostructure hydrogen storage material, what is the difficulties you found so far in your research?
Okay, thank you so much for the question. Well, if you look into the difficulties at the moment, well, as I mentioned in the slide just now, is the challenge to reduce the temperature for desorption. So that is basically, I think most of the researchers are trying to figure out how we can actually reduce the temperature, desorption temperature. Absorption is not really a problem. We able to get very high kinetics, very quick charging hydrogen to the material. However, in terms of desorption performance, we are actually trying to figure out the mechanism, trying to figure out the strategy in order for us to reduce the temperature to a lower temperature, at least to within hundreds, 150, 160 kind of range. So that is one of the challenge. Another challenge in terms of making sure that this material is going to be feasible out there is the material that we choose. Some of the materials, for example, like sodium borohydride, it able to capture as much hydrogen as possible. Yes, you can produce hydrogen using sodium borohydride. However, it has a product of the reaction. So that product of the reaction need to be considered, because whenever you have the complete system, you must make sure that this product, the byproduct, need to be managed. So that is another challenge. There is like it's sort of like a trader. Okay, you add this, you're probably going to gain this, but you probably need to work on another bit. So all in all, the complete system, okay, the complete system requires some trade-off. Okay, you could have very high hydrogen production or high hydrogen capacity, but you need to work at high temperature. So that is the trade-off. But obviously, as a researcher, we keep on searching on, a formulation, a strategy to improve that, and we look forward for more findings, inshallah.
Okay. About the condition in Malaysia, how about the fuel cell transportation system? Is it have a bright future maybe, or maybe electric car is a brighter future maybe, or what do you think?
Okay, in Malaysia is quite unique because we actually have both ends. We have electric as well as we also have fuel cell. A short term, maybe electric is very feasible, but if you were to look at long term, again, your electricity has to be supplied with some source of energy.
Yes,
still.
correct.
So if we were to look at a bigger picture and a greener solution, perhaps using hydrogen fuel cell is one way of doing it, because we only produce water out of the process, right?
Yeah.
So, but looking at the perspective of Malaysia, we also have, we already have fleets buses that runs with this hydrogen powered vehicle. We have them in Sarawak. We are actually having them ready. It's just that obviously for new things to come in, we need to, sell this idea to most of the industry so that it can be easily acceptable by all. So we look forward to more companies and more users to adapt with this hydrogen energy storage and hydrogen energy mechanism.
Okay, yeah. In your opinion, how about the price? Which one is cheaper between electric system or maybe fuel cell system?
Well, I think price is rather relative because when you talk about economics, the more you supply, the more demands that you are facing with, the price will reduce. So that is how economics system works. But in terms of the actual requirement, when we work with electric cars, it requires the battery. They still requires the battery that going to be used to charge electricity as the car is moving. So in terms of material point of view, I think both requires advanced materials as much as fuel cell requires its membranes, as much as how electric battery requires its material to allow charging of electricity over and over again. So if you ask me personally, I think both have their requirement of cost. The matter of the demand would probably going to reduce the cost in when you have lot of demand in huge bulk, so that will actually reduce. So propagating industry to accept this is one way of trying to reduce the cost as well. That's my comment.
Yes, thank you. We have one question from Tia Ayu Maharani from Vocational School Diponegoro University. Could you explain more detail the stability of hydrogen material? What is factor that influence the release of hydrogen gas? Thank you.
Thank you so much, Dia, for that question. Particularly, I'm referring to the material that I have developed, which is magnesium hydride. For magnesium hydride, it requires because it's an ionic bond. So when hydrogen is actually have a bond with magnesium, we need to supply sufficient energy, enough energy to release this hydrogen so that it can travel out from the matrices. So in this case, we noticed that from the results that we got, we are working at 300 degrees C, 260 degrees C, so that is relatively high. But if we were not to have any catalyst without any additive, we're expecting it to be like 400, 450, 450. So it's even higher. So the strategy that is used here in assisting the hydrogen to release is by creating active sites. So these catalysts are being well dispersed in the matrix of magnesium. And when this catalyst is in contact with the magnesium surface, it creates active sites where these active sites would be receiving hydrogen when it is exposed to the hydrogen atoms. So when this hydrogen in contact at the active site, it will then propagate the hydrogen absorption. As for the release, it's the other way around. So when it is receiving the right condition, for example, to overcome the barrier of the activating energy, for it to release the hydrogen, then this hydrogen are able to flow through the tubes, if you use carbon nanotubes, and eventually submerge and to the surface of the material, eventually become a hydrogen gas, released as hydrogen gas. So in terms of what actually influence the release of hydrogen gas is basically if you can overcome this activation energy, if you can shorten down, or if you can have a shortcut instead of using high energy to release the hydrogen, if you can have that enabled in the magnesium hydride system, then that would able to assist this hydrogen to be released at lower temperature. So that should able to explain what happened during the desorption process.
Okay, thank you very much, Dr. Atika. We still have time until 12:15. Maybe the participant can give the question in the chat room or directly. Maybe while waiting for the question, I want to ask Dr. Novi about the certificate of competence. Certificate of competence. As you explained before, there are many competence certificates in the oil and gas industry, and maybe the oil and gas industry also need quite a lot of certificate of competence. For the fresh graduate students, how to choose a certificate of competence that is generally applicable and can be used in maybe many kind of industry, because sometimes students also confuse which kind of certificate of competence should they choose after graduate from the vocational school. Thank you.
Okay, thank you, Ms. Utami. And competence certificate are very important in oil and gas industry. They are stated in Permen SDM nomor 5 tahun 2015. All operation in oil and gas industry must be certified. Example maybe operating a refinery or operating crude distillation unit in oil and gas industry must be competent for the operation. All country, every industry has the same technology. If you want, if you have the certificate, you can apply in Indonesia or country because the technology is same. We can expect maybe the Pertamina or multi-international in ExxonMobil or Chevron. In Indonesia, we have, in America too, and graduates can be applied to certificate competency, maybe position in operation or operator in oil and gas industry.
Last time, some certification institution offer the oil and gas industry operator certification, but they need what the student who will take the certificates, they should have practice in oil and gas industry. What do you think? But because student before they graduate, sure they don't practice in oil and gas industry. What do you think?
Okay. Student can be follow the program magang or internship in oil and gas industry. They combine to training, internship, and certificate competition. Yeah. In oil and gas industry, especially in PPSD Migas, we have training program, we have internship program, and we have a certificate program for students. In the schema for certification, we can for graduates to take the certification, but we must the training, internship, and certificate.
Oh, I see.
Magang Merdeka Belajar can be solution for the student to take certificate, because we have experience in industry. Thank you.
Okay, I see. That means that maybe students don't have to work in oil and gas industry first, or maybe if they don't work, they also still can take the certificate competence. All right. Okay.
Yes.
Okay, maybe the last question. If we only have a limited budget, and then we have to choose one certificate for the student, what kind of certificate do you think should be taken?
Okay. The budget must inland the education and inland of education and position in a competency certificate. For example, for chemical engineering or vocational school, if we want combine the program, training, internship, and certification, maybe less than for 3 million or 4 million, we can get a certificate. You have training, internship, and certificate.
I see.
That's it is free. Just pay the training and certificate.
I see. How about mechanical engineering student?
You can be the same. Just take the person for mechanical technology.
I see.
Maybe we can welding inspector or welder, or mechanical maintenance, or boiler operation. We can take. In oil and gas industry, we have.
Okay. All right. Thank you very much. Okay, we still have 15 minutes time for the question and answer session. Is there any participant who want to ask the question to the presenter? If there is no more question, maybe we can end this session. And I want to read some conclusion about the speech today from Dr. Atika. It is important to have a hydrogen storage system, which is compact, safe, and maybe also cheap in the developing fuel cell transportation system. And magnesium is a promising medium to store hydrogen and non-gaseous form. And through the presentation, a few strategies were outlined to overcome the issue, and among others is by adding catalyst range from complex catalyst to metal organic frame rope coupled with carbon nanotube. With the pressure of this catalyst, the absorption kinetic will dramatically increase as compared to the pristine magnesium. The hydrogen released at rate of 6% in 15 minutes was obtained even after running for several charging and discharging cycles. The storage material promises a competitive option to the current storage technique that offers for both mobile and stationary application. And then from Mr. Novi, soft skill characteristics. Employability skills are person ability to work in various situations and to have critical thinking skill, communicate effectively, to be highly motivated to learn and work. Employability skill can be built start from campus by improving hard skill, soft skill, personnel management, and teamwork. And hard skill can be complemented by on-campus knowledge learning, training, internship, and personal certification. Soft skill, personal management, and teamwork can be trained through active organization and soft skill training. Therefore, to be able to compete in oil and gas industry, it is not only required graduate with a high GPA, but also employability skills, which are currently needed by the industry. All right, very interesting presentation, Dr. Atika Kadri and Dr. Novi Heriono. Thank you very much for the sharing. Hopefully what has been presented is useful for all the participants. Thank you very much for joining us today. And now the session is a break session. All right. Thank you very much for all the participants who joined this sharing session today. Assalamualaikum warahmatullahi wabarakatuh.
Assalamualaikum warahmatullahi wabarakatuh.
Thank you for the moderator and sharing speakers. Let's move on to the lunch break now. Participants will be able to take a break. Please kindly to all presenters, change the name into the presenter _ room number _ full name. It will help us to identify the presentation room. We will start the presentation at 12:30. Please kindly join the breakout room meeting at 12:30. We will be greatly appreciated if participants on time. Thank you.
Diponegoro University has been moving ahead to be the best university in Indonesia by providing 13 faculties of undergraduate and postgraduate. Diponegoro University has graduated 300,000 qualified alumnus. Diponegoro University also establishes vocational schools to generate a ready-to-work alumnus. Holding the fighting values of Pangaran Diponegoro, such as honest, brave, fair and attentive, Diponegoro University keeps producing excellent alumnus nationally and internationally, while also contributing in the development of knowledge, technology, art, culture and exercise.
Diponegoro University now is a rising star. We have planned to become one of university in 500 world university rank. We have been continuously improving the supporting aspect such as regulation, facilities, financial system, bureaucracy management, information system, as well as quality of human resources, quality escalation of Tri Dharma Perguruan Tinggi is the primary target of UNDIP by stimulating the downstream of research outcomes that can be beneficially implemented for the society. We also keen to improve the quantity of national and international academic publication, as well as the number of doctorates and professors in Diponegoro University.
Now, Diponegoro University has been improving in two important aspects of achievement: institutionally and student achievement. Diponegoro University has become a world-class university by being ranked 5th amongst almost 5,000 universities in Indonesia. Meanwhile, the students' achievement in both national and international scales of prestigious events are increasing. The vision to be an eminent research university is supported by the continued increase of research funding. The total research and civil service funding in 2018 is 123.7 billion rupiah. It consists of PMBP, the National Competition Research Funding, and Collaboration Research Funding. The intellectual property right becomes the indicator of significantly improved research. The patent consists of simple patent, patent, international patent, software, and invention legal letter. To support the academic process, Diponegoro University has been improving the student facilities. Thus, the students will not only get the knowledge, but also the actualization space. As for the academic service, Diponegoro University has built a central computerized system that includes the service for the online study plan and online registration.
Iklim kompetisi di Undip yang sportif dan konstruktif memacu saya untuk terus berprestasi dalam akademik maupun non-akademik.
Didukung dengan fasilitas umum dan keakademikan yang lengkap.
Sehingga membawa Undip masuk 10 besar universitas terbaik di Indonesia.
Undip berada di daerah beragam budaya yang harmonis.
Yang pastinya Undip lebih baik.
Undip lebih baik. Bagaimanapun, Undip pasti lebih baik.
Diponegoro University has been moving ahead to be the best university in Indonesia by providing 13 faculties of undergraduate and postgraduate. Diponegoro University has graduated 300,000 qualified alumnus. Diponegoro University also establishes vocational schools to generate a ready-to-work alumnus. Holding the fighting values of Pangaran Diponegoro, such as honest, brave, fair and attentive, Diponegoro University keeps producing excellent alumnus nationally and internationally, while also contributing in the development of knowledge, technology, art, culture and exercise.
Diponegoro University now is a rising star. We have planned to become one of university in 500 World University rank. We have been continuously improving the supporting aspect such as regulation, facilities, financial system, bureaucracy management, information system, as well as quality of human resources, quality escalation of Tri Dharma perguruan tinggi is the primary target of UNED. By stimulating the downstream of research outcomes that can be beneficially implemented for the society. We are also keen to improve the quantity of national and international academic publication, as well as the number of doctorates and professors in Diponegoro University.
Now, Diponegoro University has been improving in two important aspects of achievement: institutionally and student achievement. Diponegoro University has become a world-class university by being ranked 5th amongst almost 5,000 universities in Indonesia. Meanwhile, the students' achievement in both national and international scales of prestigious events are increasing. The vision to be an eminent research university is supported by the continued increase of research funding. The total research and civil service funding in 2018 is 123.7 billion rupiah. It consists of PNBP, the National Competition Research Funding, and Collaboration Research Funding. The intellectual property right becomes the indicator of significantly improved research. The patent consists of simple patent, patent, international patent, software, and invention legal letter. To support the academic process, Diponegoro University has been improving the student facilities. Thus, the students will not only get the knowledge, but also the actualization space. As for the academic service, Diponegoro University has built a central computerized system that includes the service for the online study plan and online registration.
Iklim kompetisi di Undip yang sportif dan konstruktif memacu saya untuk terus berprestasi dalam akademik maupun non-akademik.
Didukung dengan fasilitas umum dan keakademikan yang lengkap.
Sehingga membawa Undip masuk 10 besar universitas terbaik di Indonesia.
Undip berada di daerah beragam budaya yang harmonis.
Yang pastinya Undip lebih baik.
Undip lebih baik. Bagaimanapun, Undip pasti lebih baik.
Diponegoro University has been moving ahead to be the best university in Indonesia by providing 13 faculties of undergraduate and postgraduate. Diponegoro University has graduated 300,000 qualified alumnus. Diponegoro University also establishes vocational schools to generate a ready-to-work alumnus. Holding the fighting values of Pangaran Diponegoro, such as honest, brave, fair and attentive, Diponegoro University keeps producing excellent alumnus nationally and internationally, while also contributing in the development of knowledge, technology, art, culture and exercise.
Diponegoro University now is a rising star. We have planned to become one of university in 500 World University rank. We have been continuously improving the supporting aspect such as regulation, facilities, financial system, bureaucracy management, information system, as well as quality of human resources, quality escalation of Tri Dharma Perguruan Tinggi is the primary target of Undip by stimulating the downstream of research outcomes that can be beneficially implemented for the society. We are also keen to improve the quantity of national and international academic publication, as well as the number of doctorates and professors in Diponegoro University.
Now, Diponegoro University has been improving in two important aspects of achievement: institutionally and student achievement. Diponegoro University has become a world-class university by being ranked 5th amongst almost 5,000 universities in Indonesia. Meanwhile, the students' achievement in both national and international scales of prestigious events are increasing. The vision to be an eminent research university is supported by the continued increase of research funding. The total research and civil service funding in 2018 is 123.7 billion rupiah. It consists of PNBP, the National Competition Research Funding, and Collaboration Research Funding. The intellectual property right becomes the indicator of significantly improved research. The patent consists of simple patent, patent, international patent, software, and invention legal letter. To support the academic process, Diponegoro University has been improving the student facilities. Thus, the students will not only get the knowledge, but also the actualization space. As for the academic service, Diponegoro University has built a central computerized system that includes the service for the online study plan and online registration.
Iklim kompetisi di Undip yang sportif dan konstruktif memacu saya untuk terus berprestasi dalam akademik maupun non-akademik.
Didukung dengan fasilitas umum dan keakademikan yang lengkap.
Sehingga membawa Undip masuk 10 besar universitas terbaik di Indonesia.
Undip berada di daerah beragam budaya yang harmonis.
Yang pastinya Undip lebih baik.
Undip lebih baik. Bagaimanapun, Undip pasti lebih baik.
Diponegoro University has been moving ahead to be the best university and postgraduate. Diponegoro University has graduated 300,000 qualified alumnus. Diponegoro University also establishes vocational schools to generate a ready-to-work alumnus. Holding the fighting values of Pangaran Diponegoro, such as honest, brave, fair and attentive, Diponegoro University keeps producing excellent alumnus nationally and internationally, while also contributing in the development of knowledge, technology, art, culture and exercise.
Diponegoro University now is a rising star. We have planned to become one of university in 500 World University rank. We have been continuously improving the supporting aspect such as regulation, facilities, financial system, bureaucracy management, information system, as well as quality of human resources, quality escalation of Tridharma